At the very heart of our Milky Way lurks a cosmic monster, invisible yet overwhelmingly powerful. Sagittarius A, a supermassive black hole, is the dark engine around which our entire galaxy spins. Far from being a distant abstract mystery, it's a force that warps space and time, devours anything that dares come too close, and sends shockwaves of energy across the galactic core. Astronomers watch it with a mix of awe and fear, for Sagittarius A is not just a scientific curiosity, it is the demon at the centre of our galaxy, silently shaping the fate of billions of stars, including our own Sun. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there now. Now, settle in for a journey to the most unknown object in the universe. At the very heart of our Milky Way galaxy lies a hidden giant, a supermassive black hole named Sagittarius A star. This mysterious object cannot be seen with the naked eye, but its presence dominates the centre of our galaxy. From Earth, it appears near the border between the constellations Sagittarius and Scorpius, just a few degrees south of the ecliptic, and is visually close to the butterfly cluster and the star Lambda Scorpii. Despite being invisible in ordinary light, Sagittarius A star is a bright compact source of radio waves which astronomers can detect and study. The first ever image of Sagittarius A star was unveiled on the 12th of May, 2022 by the Event Horizon Telescope collaboration. This groundbreaking image, based on data collected 5 years earlier in 2017, confirmed beyond doubt that a black hole lurks at the centre of our galaxy. It became only the second direct image of a black hole ever captured, a monumental achievement that required 5 years of meticulous calculations to process. The data came from 8 radio observatories spread across 6 different locations around the globe. By combining these observations through a technique called aperture synthesis, astronomers were able to create detailed radio images, though the task was made more challenging by the fact that Sagittarius A star's radio emissions change on the scale of mere minutes. From these observations, scientists calculated that Sagittarius A star has an angular size of about 51.8 microarc seconds, plus or minus 2.3. At a distance of 26,000 light-years, this translates to a diameter of roughly 51,800,000 kilometers, or 32,200,000 miles. To put that into perspective, Earth orbits the Sun at a distance of 150 million kilometers, while Mercury at its closest approach comes within 46 million kilometers. Sagittarius A star also drifts slowly through space, moving about negative 2.7 milliseconds per year along right ascension and negative 5.6 milliseconds per year along declination. Measurements of its gravitational influence have provided one of the most rigorous tests of Einstein's theory of relativity, and the results match his predictions perfectly. Further studies in 2019 using the high-resolution airborne wideband Camera Plus aboard NASA's SOFIA aircraft revealed that magnetic fields play a key role around Sagittarius A star. These fields shape the surrounding ring of gas and dust, whose temperatures range from nearly minus 280 degrees Fahrenheit to over 17,500 degrees Fahrenheit, or roughly minus 173 to nearly 10,000 degrees Celsius. The magnetic forces guide this matter into a steady orbit around the black hole, keeping its emissions surprisingly quiet for such a powerful object. Sagittarius A star cannot be seen in ordinary visible light, because interstellar dust and gas block about 25 magnitudes of light, scattering and absorbing it before it can reach us. The first hint of its existence came in April of 1933, when Carl Jansky, one of the pioneers of radio astronomy, detected mysterious radio signals coming from the direction of Sagittarius, pointing toward the galactic centre. Later, Jack Piddington and Harry Minette in Sydney discovered a bright, discrete radio source in the same region. Observations using larger telescopes eventually confirmed that this source likely marked the true centre of the Milky Way. Detailed study revealed that Sagittarius A is not a single object, but a cluster of overlapping sources. The brightest and most compact part, Sgr A star, was discovered in mid-February of 1974 by Bruce Ballack and Robert L. Brown at the National Radio Astronomy Observatory. The name Sgr A star was given by Brown in 1980, inspired by the idea of excited radio emissions, much like excited states of atoms are marked with an asterisk. By the 1980s, astronomers had gathered strong evidence suggesting that Sgr A star is indeed a black hole. In 1994, a team from Berkeley, including Nobel laureate Charles H. Townes and future Nobel Prize winner Reinhard Genzel, used infrared and sub-millimeter spectroscopy to estimate that its mass is concentrated at roughly 3 million times the mass of our Sun. In mid-October of 2002, Reinhard Genzel and an international team observed the motion of a nearby star, known as S2, over a 10-year period. Tracking this star's orbit revealed that Sgr A star could not be a cluster of ordinary stars or exotic compact objects. It had to be a supermassive black hole. The observations relied on near-infrared measurements, where dust interference is minimal, and used master sources as precise reference points. By studying S2's elliptical orbit, astronomers determined that Sgr A star contains about 4,100,000 solar masses, all packed into a volume no larger than 17 light-hours in radius. Later observations of other stars, like S14, confirmed similar mass and volume estimates. For reference, the Schwarzschild radius, the point of no return for a black hole, is about 0.08 astronomical units, or roughly 12 million kilometers. Determining the distance to the galactic center is crucial for calibrating cosmic measurements, and it was estimated at roughly 8,000 parsecs, or 30,000 light-years, from Earth. In November of 2004, astronomers discovered a possible intermediate mass black hole, about 1,300 times the mass of the Sun, orbiting 3 light-years from Sgr A star within a cluster of 7 stars. This may provide clues about how supermassive black holes grow by consuming smaller black holes and stars nearby. After 16 years of monitoring stellar orbits around Sgr A star, a team led by Gillison calculated its mass at roughly 4,300,000 solar masses, confirming it as one of the most compelling pieces of evidence that supermassive black holes truly exist. The results were published in 2009, and Genzel noted that the stellar motions provide proof beyond reasonable doubt that such an immense central mass must be a black hole. The black hole is not entirely silent. On the 5th of January 2015, NASA recorded an X-ray flare 400 times brighter than usual, likely caused by an asteroid being torn apart or by magnetic field entanglement in the inflowing gas. On the 13th of May 2019, astronomers observed a sudden brightening 75 times above normal levels, suggesting an encounter with another object. Even more recently, in June of 2023, unexplained filaments of radio energy were detected surrounding Sgr A star, continuing to intrigue and challenge astronomers studying the heart of our galaxy. On the 31st of October 2018, astronomers announced a remarkable discovery that finally confirmed what many had long suspected. Sagittarius A star, the mysterious heart of our Milky Way galaxy, is indeed a supermassive black hole. To achieve this breakthrough, scientists used the gravity interferometer in combination with the 4 enormous telescopes of the Very Large Telescope located in Chile. By linking these telescopes together, they effectively created a virtual telescope spanning 130 meters, almost 430 feet, across. This unprecedented resolution allowed them to detect clumps of gas swirling at mind-boggling speeds, reaching nearly 30% of the speed of light. In addition, astronomers observed 3 strikingly bright flares caused by extremely energetic electrons dancing perilously close to the black hole. These flares behaved exactly as theoretical models had predicted, tracing the paths of hotspots orbiting a black hole with a mass of about 4 million suns. Scientists believe these brilliant bursts arise from intense magnetic interactions within the scorching gas whirling near Sagittarius A star, painting a vivid portrait of a cosmic storm happening far beyond our direct view. Earlier that year, in July of 2018, another astonishing observation was reported. A star known as S2, orbiting Sagittarius A star, was recorded moving at an astonishing 7,650 kilometers per second, roughly 17.1 million miles per hour, which is about 2.5% of the speed of light. This measurement occurred as the star approached its closest point to the black hole, known as the pericenter, in May of the same year. At that moment, S2 was about 120 astronomical units away, equivalent to 18 billion kilometers, or 11 billion miles, roughly 1,400 times the Schwarzschild radius of the black hole. At such extreme proximity, Einstein's general theory of relativity predicted that the star's light would experience a noticeable gravitational redshift, adding to the usual redshift caused by its rapid motion. Remarkably, this gravitational redshift was observed and found to match Einstein's predictions within 10%, providing one more spectacular confirmation of relativity at work in the cosmos. Interestingly, the radio waves emitted by Sagittarius A star do not originate exactly from the black hole itself. Instead, they come from a bright region surrounding it, close to the event horizon. This could be part of the swirling accretion disk or a relativistic jet of material being ejected from that disk. If the radio emissions were perfectly centered on the black hole, gravitational lensing would magnify its image, creating a ring-like shape. According to general relativity, this ring would have a diameter approximately 5.2 times the Schwarzschild radius of the black hole, which translates to about 52 microarc seconds. Observations reveal that the apparent size of Sagittarius A star is very close to this, around 50 microarc seconds, while the black hole itself appears to span about 20 microarc seconds. Lower resolution observations indicate that the radio source around Sagittarius A star is symmetrical. Some alternative theories of gravity produce images that are difficult to distinguish from those predicted by general relativity. But simulations show that the symmetrical appearance and small angular size of the source are exactly what would be expected from a black hole, reinforcing the conclusion that Sagittarius A star is indeed a supermassive black hole. Scientists have estimated the mass of Sagittarius A star using multiple methods. Two groups, one in Germany and another in the United States, carefully tracked the orbits of individual stars close to the black hole. By applying Kepler's laws, they inferred the mass contained within these orbits. The German team calculated a mass of about 4.31 million suns, with a margin of error of plus or minus 380,000 solar masses. The American team found a similar value of roughly 4.1 million suns, with an uncertainty of plus or minus 600,000 solar masses. Since this mass is squeezed into a sphere only 44 million kilometers across, it produces a density 10 times higher than earlier estimates. More recent studies looked at the motions of thousands of stars within roughly 1 parsec, a little over 3 light-years, of the black hole. Using statistical techniques, astronomers estimated the black hole's mass at about 3.6 million suns, plus 200,000 and minus 400,000 solar masses, with an additional distributed mass of around 1 million suns in the same central region. This extra mass likely comes from ordinary stars and remnants of dead stars. Despite its immense mass, Sagittarius A star is relatively modest for a supermassive black hole, and its faint radio and infrared emissions indicate that the Milky Way is not an active Seyfert galaxy. Crucially, what we observe is not the black hole itself. This cosmic monster remains invisible, but rather the glowing gas and dust heated to millions of degrees as they spiral inward. The black hole itself contributes only an almost unimaginably faint Hawking radiation, around 10 to the minus 14 Kelvin, far too faint to detect. Further evidence comes from high-energy observations. The European Space Agency's Gamma Ray Observatory, Integral, detected gamma rays interacting with the nearby giant molecular cloud Sagittarius B2, which in turn produced X-ray emissions from the cloud. The total luminosity from this outburst was estimated to be roughly 1.5 times 10 to the 39th ergs per second, 1,000,000 times brighter than the current output from Sagittarius A star, and comparable to a typical active galactic nucleus. In 2011, Japanese astronomers using the Suzuku satellite confirmed these findings, strengthening the case for the black hole's influence on its surroundings. In July of 2019, astronomers reported discovering a star called S5HVS1, hurtling through space at an incredible 1,755 kilometers per second, or nearly 4 million miles per hour, about 6,000ths the speed of light. This star, located in the southern constellation Grus, or the Crane, approximately 29,000 light-years from Earth, may have been flung out of the Milky Way after a close encounter with Sagittarius A star, showcasing the black hole's immense gravitational power and its role as the ultimate cosmic slingshot. At the heart of our Milky Way galaxy lies Sagittarius A, a supermassive black hole shrouded in mystery. Orbiting perilously close to this cosmic monster is a group of stars collectively known as the S stars. These stars are anything but ordinary. They dance in dizzying paths around the black hole, their movements tracing the invisible grip of a force so powerful it warps space and time itself. Because dense clouds of interstellar dust block visible light from reaching us, astronomers study these stars using infrared light, particularly in what is called the K-band, which can pierce through the cosmic haze. The study of the S stars is a rapidly evolving field. Back in 2011, astronomers mapped the orbits of the most prominent stars known at the time, comparing their loops around Sagittarius A to the planetary orbits in our own solar system. Excitement ran high when S62 was thought to swing even closer to the black hole than any star observed before. Later observations, however, revealed that this daring approach was not quite as extreme as first believed. What makes the S stars so valuable to astronomers is their incredible speed and their proximity to the black hole. These characteristics allow scientists to measure the physical dimensions of Sagittarius A and observe the subtle effects predicted by Einstein's theory of general relativity, such as the shifting of a star's closest approach point, or periaps, in its orbit. Researchers also maintain a vigilant watch for any star that might stray too close and be torn apart by the black hole's tidal forces. But fortunately, none of these stars are expected to meet that violent fate. As of the year 2020, the current record holder for the closest approach is S4714. This extraordinary star swings to within roughly 12.6 astronomical units, about 1,880,000,000 kilometers, of Sagittarius A. To put that in perspective, this is nearly the same distance as Saturn gets from the Sun. S47, 14 rockets along at nearly 8% of the speed of light. Its orbit takes about 12 years to complete, yet its path is highly elongated, with an eccentricity of 0.985, which explains both its close approach and its astonishing velocity. Of course, these numbers come with uncertainties. The perienter distance could vary by plus or minus 9.3 astronomical units, and its speed could differ by plus or minus 8,840 km per second. Detailed tables of the S-star cluster exist, cataloguing their properties meticulously. Stars are listed with designations from different catalogues, along with standard orbital elements like the size and shape of their orbits, the tilt and orientation of their paths, and key dates such as the time of closest approach. Additional measurements include their infrared brightness and the speed and distance at their nearest points to Sagittarius A. Among the intriguing visitors to this turbulent region is the gas cloud known as G2. First spotted in 2002, G2 has a mass roughly 3 times that of the Earth. In 2012, a paper in Nature suggested that G2 was on a trajectory, taking it close to the black hole's accretion zone, the region where matter spirals inward, ultimately vanishing beyond the event horizon. Predictions indicated that G2 would reach its closest approach, or perinigricon, in early 2014 at a distance of just over 3,000 times the radius of the black hole's event horizon, roughly 260 astronomical units, or about 36 light-hours away. Observations since 2009 showed the cloud gradually being pulled apart, and some astronomers expected it might be completely destroyed, producing a spectacular brightening in X-rays and other emissions. Others speculated that G2 could hide a dim star or even be the result of a merger of 2 stars, holding it together as it passed by the black hole. In May of 2013, scientists proposed that before reaching its closest approach, G2 might have several near encounters with other stars or remnants, like neutron stars orbiting the black hole. Studying these interactions promised a rare glimpse into the extreme environment surrounding Sagittarius A. Astronomers were particularly eager to observe G2's approach because the black hole's normal accretion rate is surprisingly low for an object of its mass. Being so close to Earth allows us to detect even faint activity, and the passage of G2 offered a potential natural experiment to learn more about how supermassive black holes feed on surrounding matter. Numerous observatories focused on the event, including Chandra, XMM Newton, the Very Large Array, Integral, Swift, Fermi, and requests were made for observations with the Very Large Telescope and Keck Observatory. Simulations of the cloud's journey were prepared by teams at the European Southern Observatory and Lawrence Livermore National Laboratory. Darrell Haggard, an astronomer observing the event, remarked, "It's exciting to have something that feels more like an experiment," expressing hope that the interaction would reveal new insights into black hole physics. Yet, when the closest approach occurred in March of 2014, the event was underwhelming. No spectacular fireworks appeared. Observations on the 19th and 20th of March confirmed that G2 had survived intact, contrary to predictions for a simple gas cloud, implying that a star at its centre likely held it together. Further studies published on the 21st of July 2014, using the Very Large Telescope in Chile, suggested that G2 might not be an isolated cloud at all. Instead, it could be a dense clump within a larger, thinner stream of gas, gently influencing the black hole's accretion disk over time, rather than causing sudden bursts of brightness. This theory gained support from observations of a similar cloud, G1, which passed near the black hole 13 years earlier and followed an almost identical orbit. Together, these clouds, along with a trailing gas tail, appeared to be part of a continuous stream of matter. Finally, astronomers including Andrea Ghez proposed that G2 might not be a mere gas cloud at all. Instead, it could be the product of two stars in a binary system that had merged into a single massive star, explaining why it remained intact despite the black hole's immense tidal forces. The S-stars and passing objects like G2 are not just celestial curiosities, they are living laboratories at the edge of the most extreme environment in our galaxy, offering rare opportunities to watch the laws of physics unfold in the presence of one of the universe's most enigmatic forces. A black hole is one of the universe's most mysterious and extreme objects. It is a region in space where gravity is so incredibly strong that nothing, not even light, can escape its pull. Imagine a place where the very fabric of space and time is twisted into an inescapable trap. According to Albert Einstein's groundbreaking theory of general relativity, any mass that is packed densely enough can collapse under its own gravity to form a black hole. The invisible boundary around this cosmic trap is known as the event horizon. Cross it, and there is no turning back. Yet fascinatingly, nothing locally seems different to an object passing through. In essence, black holes are perfect cosmic shadows. They reflect no light and hide everything inside from view. Quantum physics adds an even stranger twist. In the framework known as quantum field theory, black holes are predicted to emit a faint radiation called Hawking radiation. This radiation behaves like the heat from a perfectly black object, with a temperature inversely related to the black hole's mass. For stellar black holes, those formed from collapsing stars, this temperature is unimaginably tiny, mere billionths of a degree above absolute zero, making it essentially impossible to observe directly with our current instruments. The idea of objects so massive that light could not escape is not modern at all. In the 18th century, two pioneering scientists, English clergyman John Michel and French mathematician and astronomer Pierre-Simon Laplace, first suggested that such dark stars might exist. Michel, in a short letter published in 1784, calculated that a star with the same density as our Sun, but with a radius 500 times larger, would trap all light, because the speed required to escape its gravity would exceed the speed of light. He even proposed that, while invisible, such supermassive bodies could reveal themselves by the gravitational effect they had on nearby visible stars. A little more than a decade later, in 1796, Laplace reached a similar conclusion. In his book Exposition du Système du Monde, he suggested that extremely large stars could remain hidden from view, and he even supplied a mathematical analysis at the request of astronomer Franz Xaver von Zach, which was later published in von Zach's journal. At the time, these ideas excited many scholars, who imagined invisible dark stars quietly lurking in the cosmos. However, interest waned in the early 19th century when the wave-like nature of the light became better understood. Because light was then thought to behave as a wave rather than a particle, scientists were unsure how gravity could prevent it from escaping. The first truly modern understanding of black holes emerged in 1916, when Karl Schwarzschild found a solution to Einstein's equations of general relativity that described a perfectly spherical black hole. This solution became known as the Schwarzschild metric, honouring his influential work. decades later, in 1958, physicist David Finkelstein was the first to describe a black hole as a region of space from which nothing can escape, giving the concept the meaning we use today. For a long time, black holes were seen as mere mathematical curiosities. It was not until the 1960s that theoretical work showed black holes are a natural consequence of general relativity, expected to form wherever matter is dense enough. The first black hole ever confirmed by observation was Cygnus X1, discovered independently by several researchers in 1971. Black holes typically form when massive stars exhaust their fuel and collapse at the end of their life cycle. Once formed, they can grow by pulling in surrounding gas, dust, or even other stars. Some black holes, known as supermassive black holes, contain millions or even billions of times the mass of our Sun. These giants likely form either by merging with other black holes and devouring stars, or by the direct collapse of massive gas clouds. Today, astronomers believe that nearly every galaxy hosts a supermassive black hole at its centre, quietly dominating its stellar neighbourhood. Even though black holes are invisible, their presence can be detected through the way they influence nearby matter and light. Gas and dust spiralling toward a black hole often form a bright, hot accretion disk, heated by friction to extreme temperatures, sometimes producing astonishingly bright quasars, the brightest objects in the universe. Stars that wander too close to a supermassive black hole can be torn apart in spectacular tidal disruptions, their shredded material glowing brilliantly before being consumed. By observing the motions of stars orbiting an invisible mass, astronomers can measure the black hole's mass and pinpoint its location. This method has allowed scientists to identify many stellar mass black holes in binary systems, and to confirm that the radio source known as Sagittarius A, at the heart of our Milky Way galaxy, contains a supermassive black hole weighing roughly 4,300,000 times the mass of the Sun. In the year 1915, a brilliant German physicist named Albert Einstein unveiled his groundbreaking theory of general relativity. This theory fundamentally changed our understanding of gravity, showing that it was not just a force acting at a distance, but a curvature of space-time itself. Even earlier, Einstein had demonstrated that gravity could bend the path of light, an idea that seemed almost magical at the time. Only a few months after presenting his theory, a German astronomer and physicist named Karl Schwarzschild discovered an exact solution to Einstein's equations. This solution described the gravitational field produced by a single point of mass and by a perfect spherical mass. Not long after Schwarzschild's discovery, a Dutch physicist named Johannes Droste, who was a student of the famous Hendrik Lorentz, independently arrived at the same solution for a point mass and wrote a much more detailed description of its unusual properties. This solution contained a strange feature at a particular distance from the mass, now known as the Schwarzschild radius. At this radius, some of the terms in Einstein's equations became infinite, a phenomenon physicists called a singularity. At the time, nobody really understood what this meant or what was happening at that mysterious surface. Years later, in 1924, the British astronomer Arthur Eddington showed that this singularity was not a true physical problem, but rather disappeared when the equations were expressed using a different set of coordinates. Then, in 1933, the Belgian priest and physicist Georges Lemaitre realized that the singularity at the Schwarzschild radius was simply a coordinate effect, not a physical impossibility. Even before this, in 1926, Eddington had speculated in his book about the curious possibility of a star being so dense that its radius approached the Schwarzschild radius. He noted that Einstein's theory allowed astronomers to rule out stars with absurdly high densities. For instance, he wrote that a star with a radius of 250 million kilometers could not possibly have the same density as the Sun. If it did, 3 dramatic consequences would occur. First, gravity would be so strong that not even light could escape, falling back to the star like a stone to the ground. Second, the light from the star would be redshifted so much that its spectrum would vanish entirely. And third, the star's mass would warp space-time so severely that space itself would effectively close around it, leaving outside observers in nowhere. Then, in 1931, a young Indian-American physicist named Subrahmanyan Chandrasekhar applied the principles of special relativity to show that any non-rotating star made of electron-degenerate matter above a certain mass could not remain stable. This mass limit, later named the Chandrasekhar limit, was about 1.4 times the mass of the Sun. Chandrasekhar's conclusions were controversial at the time, with prominent scientists like Eddington and Lev Landau arguing that some unknown mechanism would prevent such stars from collapsing. They were partially correct. A white dwarf slightly heavier than this limit would collapse into a neutron star, which could then remain stable under its own gravity. In 1939, American physicists Robert Oppenheimer and George Volkoff extended this work. They predicted that neutron stars exceeding a critical mass, now called the Tolman-Oppenheimer Volkoff limit, would collapse even further. Using the same reasoning as Chandrasekhar, they concluded that nothing in known physics could stop at least some stars from collapsing into black holes. Their initial calculations, based on the Pauli exclusion principle, suggested this limit was about 0.7 times the mass of the Sun. Later, taking into account the strong nuclear force that causes neutrons to repel each other, the estimated range rose to roughly 1.5 to 3 times the mass of the Sun. Modern observations, such as the famous neutron star merger known as GW 17017, which likely formed a black hole shortly afterward, have refined the Tolman-Oppenheimer Volkoff limit to about 2.17 solar masses. Oppenheimer and his colleagues also proposed that the singularity at the Schwarzschild radius could be seen as the boundary of a region where time effectively stops, but only for outside observers. For anyone falling into the collapsing star, time would continue normally. Because of this, these theoretical objects were called frozen stars, since an external observer would see the star's surface frozen in time as it reached the Schwarzschild radius. Ironically, in the same year of 1939, Einstein himself tried to argue that black holes could not exist. In his paper, On a Stationary System with Spherical Symmetry, consisting of many gravitating masses, he used his general relativity equations to defend this position. Yet, only months later, Oppenheimer and his student Hartland Snyder published a groundbreaking paper titled On Continued Gravitational Contraction, which predicted the very existence of black holes. They used Einstein's own theory to show, for the first time in modern physics, the precise conditions under which a black hole could form, without ever mentioning Einstein's earlier skeptical paper. It took almost 2 decades more for the concept of a black hole's event horizon to be fully understood. In 1958, American physicist David Finkelstein identified the Schwarzschild radius as an event horizon, a one-way surface through which anything, even light, could enter but never escape. Finkelstein developed a new framework to describe the perspective of observers falling into the black hole, extending Schwarzschild's solution to include their experience. A similar approach had been found earlier by Martin Kruskal, but its importance was not fully recognized at the time. Later, the Kruskal-Sekeres coordinates became essential in helping physicists understand black holes from multiple perspectives, finally uniting the external and infalling views into a coherent picture. The period stretching roughly from the middle of the 1960s to the middle of the 1970s is often celebrated as the golden age of black hole research. During these years, black holes and Einstein's theory of general relativity leapt from being niche, abstract curiosities to central mainstream subjects in the world of physics. It was an era of remarkable discoveries, bold theoretical breakthroughs, and the gradual merging of theory with observation, a time when the universe's darkest mysteries began to shine in the minds of scientists. In this exciting decade, physicists discovered more general solutions to the equations that describe black holes. In 1963, the brilliant mathematician Roy Kerr found the exact solution for a black hole that spins, showing how rotation shapes the very fabric of space-time around it. Just 2 years later, in 1965, Ezra Newman extended this idea further by finding a solution for a black hole that both spins and carries an electric charge. These discoveries opened the door to a deeper understanding of the strange objects predicted by Einstein's theory. Around the same time, the concept of the no-hair theorem began to take shape through the work of Werner Israel, Brandon Carter, and David Robinson. This elegant theorem proposed that a stationary black hole could be fully described by only 3 properties: its mass, its spin, and its electric charge. Everything else about the black hole's origin or the matter that formed it seemed to vanish beyond the event horizon, leaving behind a deceptively simple yet deeply mysterious object. Initially, many scientists wondered if the odd features of these black hole solutions, the so-called singularities, points where density and gravity become infinite, were just artifacts of the idealized, symmetrical conditions imposed in the equations. Notably, Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz argued that these singularities would never appear in more general, real-world scenarios. Yet, by the late 1960s, Roger Penrose and Stephen Hawking used powerful global mathematical techniques to show that singularities are not just theoretical quirks. They appear naturally in the evolution of massive stars and collapsing matter. For his contributions, Roger Penrose was awarded half of the Nobel Prize in Physics in 2020, while Stephen Hawking, having passed away in 2018, was ineligible for the honour. This period was not only revolutionary on the theoretical front. Astronomical observations leapt forward as well. In 1967, Anthony Hewish and Jocelyn Bell Burnell discovered pulsars, spinning stars that emit regular pulses of radiation. By 1969, these objects were recognised as rapidly rotating neutron stars, dense, compact remnants of massive stars that had exploded in supernovae. Until then, neutron stars, like black holes, had largely been considered theoretical oddities. The discovery of pulsars, however, confirmed their physical reality and sparked immense interest in compact cosmic objects formed by gravitational collapse. In the early 1970s, astronomers in Greenwich and Toronto studied Cygnus X1, a mysterious X-ray source first detected in 1964. Observations suggested that it was the first astronomical object widely accepted as a black hole, a remarkable step toward connecting theoretical predictions with real celestial bodies. During the same years, theorists including James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking developed the laws of black hole thermodynamics. These laws showed that black holes, though seemingly simple and featureless, obey principles analogous to the familiar laws of heat and energy. Mass could be related to energy, the surface area of a black hole's horizon to entropy, and surface gravity to temperature. The analogy became literal in 1974 when Hawking demonstrated that black holes should emit radiation, now famously called Hawking radiation, behaving like a glowing black body with a temperature linked to their gravitational pull. The exploration of black holes leapt even further into the modern era. On the 11th of February 2016, the LIGO Scientific Collaboration and the Virgo Collaboration announced the first direct detection of gravitational waves, the ripples in spacetime caused by the collision of two black holes. Just a few years later, on the 10th of April 2019, the first direct image of a black hole and its surrounding region was revealed, based on observations made in 2017 by the Event Horizon Telescope. This image captured the supermassive black hole at the heart of the galaxy Messier 87, providing a visual confirmation of these enigmatic giants. Closer to home, the European Gaia mission revealed even more surprises. Among its findings were a Sun-like star orbiting a black hole named Gaia BH1, approximately 1,560 light-years away, and a possible brown dwarf star orbiting Gaia BH2. Although only a few dozen black holes have been directly detected in the Milky Way so far, astronomers estimate that hundreds of millions exist. Most are solitary wanderers, invisible except through the subtle bending of light around them, a phenomenon known as gravitational lensing. The evocative term black hole itself emerged during this golden age. In December 1967, a student reportedly suggested the phrase during a lecture by the legendary physicist John Wheeler, who quickly adopted it for its simplicity and striking imagery. Wheeler's stature in the field helped the term gain widespread acceptance. However, the origins of the phrase are somewhat murky. Science writer Marcia Bartusiak traces its roots to physicist Robert H. Dicke, who, in the early 1960s, reportedly likened these objects to the infamous Black Hole of Calcutta, a prison where those who entered never left alive. The term had even appeared in print by 1963 in Life and Science news magazines, and in a January 18, 1964, article by science journalist Anne Ewing titled "Black Holes in Space," which reported on a meeting of the American Association for the Advancement of Science in Cleveland, Ohio. Thus, the mid-60s to mid-70s were a period of extraordinary intellectual adventure, where theoretical audacity met observational ingenuity. Black holes, once imagined as mathematical curiosities, became tangible pillars of modern astrophysics, captivating the imagination of scientists and the public alike. A black hole is an object in space so extreme that its gravitational pull is stronger than the speed of light itself, meaning nothing, not even light, can escape once it gets too close. In technical terms, a black hole is any object whose mass is packed within a certain critical radius, called the Schwarzschild radius. This radius comes from a solution to Albert Einstein's equations of general relativity. One of the most fascinating ideas about black holes is known as the no-hair theorem. This principle suggests that, after a black hole settles down following its formation, it can be fully described by just three properties: its mass, its electric charge, and its spin, or angular momentum. Beyond these three, a black hole is essentially featureless. If this idea holds perfectly, then two black holes with identical mass, charge, and spin would be completely indistinguishable from each other. Scientists are still investigating exactly how true this is for real black holes in our universe. What makes these properties special is that they can be observed from a distance. For example, a charged black hole will repel other objects with the same type of charge, just like any normal charged object. Similarly, the total mass of a black hole can be measured far away using techniques derived from gravity, similar to Gauss's law in electromagnetism. Even the spin of a black hole can be detected from afar by observing how it drags the surrounding space around it, a phenomenon called frame dragging, which can be measured through effects such as the lens-thirring effect. When something falls into a black hole, any information about its shape or how its charge was distributed gets smeared out along the black hole's event horizon, becoming inaccessible to outside observers. The horizon itself behaves like a stretched, conductive and slightly sticky membrane with friction and electrical resistance. This membrane paradigm is quite different from ordinary field theories, like electromagnetism, where effects are perfectly reversible at small scales. Because a black hole eventually stabilizes with only these three visible properties, most of the information about what went into it is lost. This includes quantities like the total number of protons and neutrons, baryon number, or electrons and neutrinos, lepton number, that cannot be measured from outside. This puzzling disappearance of information is called the black hole information loss paradox, and it remains one of the most mysterious problems in physics. The simplest kind of black hole has only mass and neither electric charge nor spin. These are called Schwarzschild black holes, named after the German physicist Karl Schwarzschild, who discovered this solution in the year 1916. According to Birkhoff's theorem, a Schwarzschild black hole is the only solution that is perfectly spherical in a vacuum. This means that, from a distance, its gravitational field looks exactly like that of any other spherical object with the same mass. The popular idea that a black hole sucks in everything around it is therefore only true very close to the event horizon. Far away, it behaves like any ordinary massive object. More complex black holes are also possible. A non-rotating but electrically charged black hole is described by the Reissner-Nordström solution. A spinning but neutral black hole is described by the Kerr solution. The most general known type of black hole, which can have both spin and charge, is described by the Kerr-Newman solution. While a black hole's mass can be any positive value, its charge and spin are limited by its mass. Black holes that have the maximum allowed charge or spin for their mass are called extremal. There are theoretical solutions that violate these limits, but they lack an event horizon and have naked singularities visible from the outside. These are considered unphysical because realistic matter collapsing under gravity cannot produce them, a principle known as the cosmic censorship hypothesis, supported by computer simulations. Most black holes formed from stars are expected to have almost no electric charge, because stars themselves are nearly neutral. However, rotation is very common among compact objects, including black holes. For example, the black hole candidate in the X-ray binary system GRS 1915 + 105 seems to spin near the maximum allowed rate. Scientists often use this limit to define a dimensionless spin parameter to describe how fast a black hole rotates. Black holes are often classified by their mass. The size of a black hole, measured by the radius of its event horizon or Schwarzschild radius, is directly proportional to its mass. For a black hole with spin or electric charge, the radius becomes smaller, with extremal black holes having event horizons that shrink dramatically compared to their Schwarzschild radius. The most defining characteristic of a black hole is something called the event horizon. Think of it as an invisible boundary in the fabric of space and time surrounding the black hole. Once anything, whether it's matter, dust, or even light, crosses this boundary, there is no turning back. Nothing can escape its pull. The term event horizon is used because any event that happens inside this boundary is forever hidden from the rest of the universe. No information about it can reach an outside observer, making it impossible to know if it happened at all. According to Albert Einstein's theory of general relativity, mass bends the fabric of space-time, and this bending directs the paths of particles towards the mass. Around a black hole, this bending grows so extreme that at the event horizon, all paths point inward. There simply aren't any routes that lead away from the black hole. If we imagine observing a black hole from a distance, clocks near it would seem to tick more slowly compared to clocks far away. This effect, known as gravitational time dilation, would also make an object falling into the black hole appear to slow down as it nears the event horizon. From our perspective, it would take an infinite amount of time for the object to reach the edge. Every process on that object seems to slow down, and any light it emits shifts to longer wavelengths, appearing redder and dimmer. Eventually, the falling object fades from view entirely, often vanishing in less than a second. However, for a hypothetical observer who could fall into the black hole unharmed, none of this would seem unusual. Their own clock would tick normally, and they would cross the event horizon in a finite amount of time without noticing anything peculiar. According to general relativity, the event horizon cannot be detected by any local measurements, due to the principle of equivalence that Einstein described. The shape of a black hole's event horizon is always round, like a sphere. For black holes that are not spinning, the event horizon is perfectly spherical. But if a black hole rotates, the event horizon becomes slightly flattened, or oblate, at the poles. At the very centre of a black hole, according to the simplest model developed by Carl Schwarzschild, lies a gravitational singularity, a point where the curvature of space-time becomes infinite. In a non-rotating black hole, this singularity is a single point. In a rotating black hole, it stretches into a ring lying in the plane of rotation. In both cases, this central region has zero volume but contains all the black hole's mass, giving it infinite density. Even though the Schwarzschild model breaks down exactly at the singularity, anyone or anything that crosses the event horizon of a non-rotating, uncharged black hole cannot avoid being pulled into it. They can attempt to slow their fall by accelerating away, but only for a limited time. Eventually they are crushed to infinite density, and their mass is absorbed into the black hole. Before reaching the singularity, tidal forces stretch and compress the object, in a process vividly nicknamed spaghettification. In more complex black holes, such as those that are charged or rotating, there are theoretical scenarios where it might be possible to avoid the singularity entirely. These solutions suggest that black holes could act like wormholes, potentially connecting to another region of space-time or even a different universe. Some theories also allow for closed time-like curves, paths that could theoretically loop back in time, creating paradoxes like the famous grandfather paradox. However, these effects are purely theoretical, and even a tiny disturbance would destroy them. Most physicists believe that a true theory combining quantum mechanics and gravity would eliminate such extreme possibilities. The appearance of singularities in general relativity signals a breakdown of the theory, indicating that the effects of quantum mechanics become essential at extremely high densities. So far, scientists have not been able to unite gravity and quantum mechanics into a single framework, though attempts to create a theory of quantum gravity continue. Most experts expect that such a theory would avoid the concept of infinite density altogether. An alternative view comes from string theory, in a model called the fuzzball model. Here, the internal structure of a black hole does not have a singularity or even a traditional event horizon. Yet, for an outside observer, the collective behaviour of these fuzzball states appears just like a normal black hole, as predicted by general relativity. Around a black hole lies a remarkable and mysterious region called the Photon Sphere. This is a spherical boundary where light, in the form of photons, can orbit the black hole in a circle, though this orbit is far from stable. For a black hole that does not rotate, the photon sphere lies at a distance equal to 1.5 times the Schwarzschild radius of the black hole. Photons here are in a delicate balancing act. Any tiny disturbance, such as a passing particle or a slight gravitational nudge, can tip them off course. This means a photon might either spiral outward, escaping into space, or fall inward, crossing the event horizon and disappearing forever into the black hole. Even though light can temporarily circle the black hole at the photon sphere, any light moving inward past this boundary is doomed to be captured. Therefore, any light that reaches a distant observer must come from objects located in the thin layer between the photon sphere and the event horizon, the invisible point of no return. For rotating, or Kerr, black holes, the situation becomes even more complex. The radius of the photon sphere depends on how fast the black hole spins and the direction of the photon's orbit. Photons can orbit in the same direction as the black hole's spin, known as prograde, or in the opposite direction, called retrograde, and each case creates a slightly different orbit. Rotating black holes are further surrounded by an extraordinary region called the Ergosphere, where the very fabric of space-time is twisted and dragged along by the black hole's spin. This effect, known as frame dragging, is a prediction of Einstein's theory of general relativity. Essentially, any object near the black hole is compelled to move in the direction of its rotation. Near the event horizon, the effect becomes so extreme that to remain stationary relative to distant space, an object would need to move faster than the speed of light in the opposite direction, an impossibility. The shape of the ergosphere is unique. It touches the event horizon at the black hole's poles but bulges outward around the equator, forming a kind of cosmic oblate spheroid. Unlike the event horizon, objects and radiation can still escape from the ergosphere. Amazingly, through a mechanism known as the Penrose process, objects entering the ergosphere can leave with more energy than they had when they arrived. This extra energy comes from the black hole's rotation, which gradually slows down as it transfers rotational energy to matter and light. In regions with strong magnetic fields, a variant called the Blandford-Znajek process is believed to power the dazzling luminosity and high-speed jets seen in quasars and other active galactic nuclei. In the familiar world of Newtonian gravity, objects can orbit stably at almost any distance from a massive body. General relativity, however, imposes a limit. There exists an innermost stable circular orbit, often called the Sgr. Any slight inward push from this orbit will send matter spiraling into the black hole, while outward nudges may result in complex paths, spiraling stable oscillations, or escape into space, depending on the object's energy. For rotating black holes, the radius of the Sgr depends on the direction of the orbit relative to the spin. It becomes smaller for orbits that move in the same direction as the black hole's rotation. Even closer to the black hole lies the plunging region, where no stable orbit is possible. Matter entering this zone can no longer circle the black hole or resist its pull. Instead, it plunges inward at incredible speeds, approaching the speed of light, until it vanishes beyond the event horizon into the ultimate abyss of the black hole. For a long time, the strange and almost mystical nature of black holes made scientists wonder whether they truly exist in the universe, or if they were simply mathematical oddities, peculiar solutions to Einstein's equations that had no real counterpart in nature. Even Albert Einstein himself believed that black holes could never actually form. He thought that the spinning motion, or angular momentum of collapsing particles would stabilize them at some radius, preventing the creation of a point of no return. Because of this, for many years the community of physicists studying general relativity largely dismissed any claim suggesting that black holes were real. Yet, a small but persistent group of relativists, physicists who specialized in Einstein's theory, argued that black holes could indeed be physical objects. By the late 1960s, their careful arguments had convinced most researchers that nothing in the laws of physics prevents an event horizon, the defining boundary of a black hole, from forming. The mathematician Roger Penrose showed that once an event horizon appears, general relativity predicts that a singularity, a point where gravity becomes infinitely strong, must form at the core, unless quantum mechanics comes into play. Not long after, Stephen Hawking demonstrated that the universe itself, in many cosmological models describing the Big Bang, also contains singularities, even without any exotic matter like scalar fields. Meanwhile, the discovery of the Kerr solution, describing rotating black holes, the no-hair theorem, showing black holes have remarkably simple properties, and the laws of black hole thermodynamics all helped establish that black holes, despite their strangeness, are elegant and understandable objects worthy of scientific study. Typically, black holes form when very massive stars undergo gravitational collapse. This occurs when the pressure inside an object is no longer strong enough to resist its own gravity. In stars, this can happen in two main ways. Either the star has exhausted nearly all its nuclear fuel and can no longer generate the heat required to support itself, or a previously stable star gains extra mass without increasing its core temperature. In either case, the star can no longer resist its own weight, and it begins to collapse. Sometimes this collapse is temporarily halted by a phenomenon known as degeneracy pressure, which is a quantum mechanical effect arising from the star's densely packed particles. When this happens, the star condenses into one of several types of compact stars, such as white dwarfs or neutron stars. Which type emerges depends largely on the mass of the leftover core after the star sheds its outer layers, for example during a Type II supernova explosion. Often, this remnant mass is significantly smaller than the star's original mass. Stars that begin with more than 20 times the mass of our Sun can leave behind remnants exceeding 5 times the mass of the Sun. If a remnant's mass surpasses roughly 3 to 4 times the mass of the Sun, a threshold known as the Tolman-Oppenheimer Limit, even the pressure from densely packed neutrons cannot stop the collapse. No known force, except perhaps quark degeneracy pressure, is sufficient to halt the implosion, and the object inevitably collapses into a black hole. In the early universe, when stars first began to form, some were extremely massive. Their collapse would have produced black holes as heavy as 1,000 times the mass of the Sun. These early black holes may have served as seeds for the supermassive black holes that now lie at the centers of most galaxies. Some theories also suggest that enormous black holes weighing around 100,000 times the mass of the Sun could have formed directly from the collapse of dense gas clouds in the young universe. These massive black holes might have been the progenitors of the first quasars, the extremely bright objects observed already when the universe was less than 1 billion years old. Observations of the young universe have identified some candidates for these ancient behemoths. Although most of the energy released during a star's gravitational collapse happens rapidly, an outside observer never truly sees the collapse finish. From the perspective of matter falling in, the collapse takes a finite amount of time. However, due to the extreme warping of space-time near the event horizon, a phenomenon known as gravitational time dilation, an external observer sees the infalling material slow down, seeming to hover just above the event horizon. The light emitted by this material becomes increasingly red-shifted and faint, fading gradually into darkness. In effect, from afar, the formation of the event horizon appears never-ending. Gravitational collapse requires extremely high densities. Today, such densities are found only in stars. But shortly after the Big Bang, densities were far higher, potentially allowing black holes to form directly from regions of overdense matter. These primordial black holes could form only where initial density fluctuations existed, letting gravity gather matter into compact regions. Different models of the early universe predict wildly varying sizes for these black holes, ranging from the unimaginably small Planck mass to hundreds of thousands of times the mass of the Sun. Despite these immense densities, the universe itself did not collapse into a single black hole during the Big Bang because the rate of cosmic expansion exceeded gravitational attraction. According to inflation theory, general relativity predicts that gravity slows the expansion, but the overall effect of negative pressure produces a repulsive gravitational field, allowing the universe to continue expanding. It's important to note that models of gravitational collapse for static objects like stars do not translate directly to the rapidly expanding cosmos of the early universe. Black holes are usually thought of as forming from the gravitational collapse of massive stars, but this is not the only way they could, in theory, come into existence. In principle, black holes could also be created during extremely high-energy collisions if the density in the collision becomes high enough. However, as of the year 2002, no such events have been observed, neither directly nor indirectly, such as through missing mass in particle accelerator experiments. This lack of observation implies that there is likely a minimum mass for black holes to exist. According to theoretical predictions, this lower limit is expected to be around the Planck mass. a scale at which the strange rules of quantum mechanics start to interfere with the classical predictions of general relativity. This means that forming black holes through any process happening on or near Earth is essentially impossible. Yet, some speculative ideas in quantum gravity hint that the smallest possible black holes could be much lighter. For instance, certain brane-world models suggest that the minimum mass could be as low as 1 tera-electronvolt divided by the speed of light squared. If these models are accurate, then tiny micro-black holes might be produced when extremely energetic cosmic rays strike Earth's atmosphere, or even inside powerful machines like the Large Hadron Collider at CERN. Nevertheless, these ideas remain highly speculative, and most experts believe the formation of black holes in these scenarios is extremely unlikely. Even if such micro-black holes could form, they would evaporate almost instantly, in around 1/10 millionth of 1 billionth of a billionth of a second, posing absolutely no threat to our planet. Once a black hole does form, it can continue to grow by absorbing surrounding matter. All black holes pull in gas, dust, and other material from their cosmic neighborhoods. This slow accumulation of matter is one possible way that supermassive black holes, which can contain millions or even billions of times the mass of the Sun, may have formed, though scientists are still trying to fully understand the process. A similar mechanism could explain the formation of intermediate mass black holes found in dense star clusters known as globular clusters. Black holes can also grow by merging with other objects, ranging from stars to other black holes. Such mergers were likely important in the early growth of supermassive black holes, as they may have formed from the gathering of many smaller black holes and massive stars. The same process might explain some of the intermediate mass black holes we observe today. In the year 1974, the brilliant physicist Stephen Hawking made a remarkable prediction. Black holes are not completely black. Instead, they slowly emit tiny amounts of thermal radiation, a phenomenon now known as Hawking radiation. By applying quantum field theory to a static black hole, Hawking showed that black holes should radiate particles with a perfect blackbody spectrum, as if they were faint glowing objects. Since then, numerous other physicists have verified his results using different theoretical approaches. If Hawking's theory is correct, black holes are not eternal. They gradually lose mass through this radiation and can eventually evaporate completely. The intensity of this radiation, often described by the Hawking temperature, depends on the black hole's surface gravity. For a simple non-rotating black hole, the temperature is inversely proportional to its mass. The larger the black hole, the colder it is, and the smaller the black hole, the hotter it becomes. For example, a black hole with the mass of the Sun would have a Hawking temperature of just 62 nanokelvins, far colder than the 2.7 Kelvin temperature of the cosmic microwave background radiation that fills space. Such black holes actually gain more mass from this cosmic background than they lose to Hawking radiation, meaning they grow instead of shrinking. To emit more radiation than they absorb, a black hole would need to weigh less than the Moon, making it smaller than 1/10 of a millimeter in diameter. Extremely small black holes, however, behave very differently. A black hole with the mass of a typical car would have a diameter of roughly 1/10 billionth of a billionth of a meter and would evaporate in a mere nanosecond, briefly shining with more than 200 times the luminosity of the Sun. Even smaller black holes, such as one with a mass of 1 tera-electronvolt divided by the speed of light squared, would disappear almost instantaneously, in less than 1/10 billionth of a trillionth of a trillionth of a trillionth of a second. At these tiny scales, quantum gravity effects are expected to dominate, and while some theories suggest they could stabilize such black holes, current research does not support this idea. For astrophysical black holes, those formed from stars or larger structures, the Hawking radiation is predicted to be incredibly faint, making it almost impossible to detect from Earth. The only potential exception is the final burst of gamma rays that might be emitted when primordial black holes, hypothetical remnants from the early universe, evaporate. So far, searches for such bursts have come up empty, providing strict limits on the existence of low-mass primordial black holes. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, continues the hunt for these elusive flashes of energy. If black holes truly evaporate via Hawking radiation, the timeline is unimaginably long. A black hole with the mass of the Sun would take around 1064 Google years, one followed by 1064 zeros, to evaporate beginning only when the temperature of the cosmic microwave background falls below that of the black hole itself. A supermassive black hole with a mass of 100 billion suns would evaporate in approximately 2 × 10 to the 100th power years. During the eventual collapse of a supercluster of galaxies, supermassive black holes might grow to masses around 100 trillion suns, yet even these gargantuan objects would eventually evaporate over a span reaching up to 10 to 106 years. By their very nature, black holes do not emit any light or other forms of electromagnetic radiation on their own, except for the hypothetical Hawking radiation, which remains undetected. This means that astronomers cannot simply see a black hole in the usual sense. Instead, they have to rely on indirect clues to prove their existence. One of the main ways this is done is by observing the gravitational influence of a black hole on nearby stars, gas, or other matter. When something is being pulled or accelerated by an unseen massive object, that can be a sign that a black hole is present. One of the most ambitious projects in this quest is the Event Horizon Telescope, or EHT, a global network of radio observatories working together to observe the regions immediately surrounding black holes' event horizons. The event horizon is the point of no return around a black hole, where nothing can escape, not even light. In April of 2017, the EHT began observing the supermassive black hole at the centre of the galaxy Messier 87, located in the Virgo cluster. To gather the necessary data, 8 radio observatories on 6 mountains across 4 continents observed the galaxy for about 10 days. After 2 years of painstaking data processing in April of 2019, the EHT team released the first ever image of a black hole. Interestingly, the black hole itself appears completely dark in the image because no light escapes from inside the event horizon. What we actually see is the glowing gas swirling just outside this boundary. These gases shine in shades of orange and red, forming a ring that reveals the black hole's presence and structure. Following this success, on the 12th of May 2022, the EHT released the first image of Sagittarius A, the supermassive black hole at the centre of our own Milky Way galaxy. The image displayed a similar ring-like shape and shadow to what was seen in the Messier 87 black hole, consistent with theoretical predictions of how light behaves near a black hole. Producing this image was much more challenging because Sagittarius A is over 1,000 times smaller and less massive than Messier 87, and the surrounding environment is highly unstable. The image was partially blurred due to turbulent plasma between Earth and the galactic centre, which interfered with longer wavelength observations. Some areas of the ring appear brighter due to Doppler beaming, an effect where material moving towards the observer at near-light speeds looks brighter than material moving away. In the case of black holes, this shows that the gas is orbiting at extremely high speeds, over 1,000 kilometers per second, or about 2,200,000 miles per hour. These speeds are necessary to balance the black hole's intense gravity and remain in orbit above the event horizon. From the brightness and orientation of the ring, astronomers could deduce that the Messier 87 black hole was observed nearly edge-on, with its accretion disk rotating clockwise. Gravity also bends the light emitted from the far side of the accretion disk around the black hole, producing extreme gravitational lensing. This effect creates the illusion that the observer is looking from above, even though the light has travelled around the black hole's curvature to reach the telescope. In addition to imaging, the EHT detected magnetic fields near the event horizon of Sagittarius A in 2015. These fields, which thread through the accretion disk, were a mixture of ordered and tangled patterns, exactly as theoretical models of black holes had predicted. In April of 2023, the EHT released a remarkable image showing both the shadow of the Messier 87 black hole and its high-energy jet together for the first time, offering an even more complete view of these extreme cosmic objects. Meanwhile, another major breakthrough in black hole research came on the 14th of September 2015, when the LIGO Gravitational Wave Observatory detected gravitational waves for the first time. These ripples in space-time match predictions for waves produced by the merger of 2 black holes, one roughly 36 times the mass of the Sun, the other about 29 solar masses. Before merging, these black holes were separated by only 350 kilometers, roughly 4 times the Schwarzschild radius for objects of those masses, confirming that they were extremely compact. LIGO's detection also captured the post-merger ringdown, the signal emitted as the newly formed black hole settles into a stable state. By analysing the frequency and decay of this signal, astronomers could determine the mass and spin of the resulting black hole, which perfectly match numerical simulations. This also confirmed the existence of the Photon Sphere, the unstable region around a black hole where light can orbit. Beyond that, these observations provided the first solid evidence for stellar mass black hole binaries, and for black holes with masses greater than 25 times that of the Sun. Since that initial detection, many more gravitational wave events have been observed. Closer to home, astronomers have tracked the motions of stars near the centre of the Milky Way, finding strong evidence that they orbit an invisible supermassive black hole, coinciding with the radio source Sagittarius A. Beginning in 1995, 90 stars were monitored, and by 1998, calculations showed that an object of about 2,600,000 solar masses must exist within a tiny region of radius about 0.02 light-years to account for the observed orbits. As one star, called S2, completed a full orbit, astronomers refined the mass estimate to about 4,300,000 solar masses contained within a region smaller than 0.002 light-years. Although this upper limit is still larger than the Schwarzschild radius, no other known object could pack so much mass into such a small space, strongly suggesting that the central object is indeed a supermassive black hole. Some observations even hint that it possesses an event horizon, a defining feature unique to black holes. As gas falls toward a black hole, it conserves angular momentum, forming a disc-like structure known as an accretion disc. Friction within the disc allows gas to spiral inward, releasing enormous amounts of potential energy and heating the gas to extremely high temperatures. Near the black hole, the inner disk rotates at phenomenal speeds, producing intense X-ray radiation detectable by telescopes. This process of accretion is remarkably efficient, converting up to 40% of the mass of the infalling gas into energy, a far greater efficiency than nuclear fusion, which converts only about 0.7% of mass into energy. Many accretion disks also produce relativistic jets along the poles, shooting energy into space, though the precise mechanisms behind these jets remain uncertain. These processes power some of the universe's most energetic phenomena. Active galactic nuclei and quasars are thought to be powered by the accretion of matter onto supermassive black holes, while X-ray binaries are generally binary systems where one star is a compact object feeding on its companion. Some ultraluminous X-ray sources may even represent intermediate mass black holes. Occasionally, stars that wander too close to supermassive black holes are torn apart by immense tidal forces in events known as tidal disruption events. The shredded material forms an accretion disk, emitting observable radiation. In November of 2011, astronomers directly observed a quasar's accretion disk around a supermassive black hole for the first time, confirming these violent and energetic processes in action. X-ray binaries are fascinating cosmic pairs of stars in which most of the energy they emit comes out in the form of X-rays. These X-rays are generally produced when one of the stars, often a small but incredibly dense object like a neutron star or black hole, pulls in gas and material from its companion star, which is a more ordinary star like our Sun. The presence of a normal star in such a system is extremely valuable for astronomers, because by studying it, they can gather information about the hidden, compact star, and even figure out whether it might be a black hole. If the system emits signals that can be traced directly back to the compact object, then it cannot be a black hole, because black holes, by their very nature, do not emit light or signals from their interiors. However, if such signals are absent, it does not automatically confirm the compact object is a black hole, since it could still be a neutron star. By carefully observing the companion star, astronomers can determine the orbital characteristics of the binary system and estimate the mass of the unseen object. If the mass of this compact object turns out to be much larger than what a neutron star can possibly hold, technically beyond the Tolman-Oppenheimer limit, then the object is almost certainly a black hole. The first strong candidate for a black hole discovered in this way was Cygnus X1, identified in the year 1972 by Charles Thomas Bolton, Louise Webster, and Paul Murdin. Early on, some doubts lingered because the companion star in the system was much more massive than the suspected black hole, making precise measurements difficult. Today, astronomers often find better black hole candidates in a special type of X-ray binary known as a soft X-ray transient. In these systems, the companion star is relatively lightweight, allowing for much more accurate estimates of the black hole's mass. These systems are particularly interesting because they only shine strongly in X-rays for a few months at a time, usually once every 10 to 50 years. During the quiet periods, called quiescence, the accretion disk around the compact object dims considerably, enabling astronomers to study the companion star in detail. One of the most famous examples of such a system is V404 Cygni. Sometimes the X-rays from these accretion disks flicker in a rhythmic pattern known as quasi-periodic oscillations. These flickers are thought to be caused by matter moving around the inner edge of the disk, very close to the innermost stable orbit around the compact object. Because the frequency of these flickers depends on the mass of the compact object, astronomers can use them as an alternative method to estimate the mass of black hole candidates. On a much larger scale, astronomers have observed galaxies that behave unusually, with intense light across many wavelengths and extremely strong radio emissions. These galaxies are called active galaxies, and scientists have discovered that the strange activity at their centers, known as active galactic nuclei, is often caused by supermassive black holes. These monsters can be millions or even billions of times more massive than our Sun. Around them forms a glowing accretion disk of gas and dust, and from the poles of this disk narrow jets of material shoot out at incredible speeds. Although supermassive black holes are expected to lie at the center of nearly all galaxies, astronomers have carefully studied only some of them to measure the black hole's actual masses. Among the best-known galaxies with strong evidence of supermassive black holes are the Andromeda Galaxy, M32, M87, NGC 3115, NGC 3377, NGC 4258, NGC 4889, NGC 1277, OJ 287, APM 08279 plus 5255, and the Sgr A Galaxy. It is now widely accepted that nearly every galaxy, even those that are not active, hosts a supermassive black hole at its center. Observations show a remarkable correlation between the mass of these black holes and the motion of stars in the galaxy's central bulge, suggesting that the formation of the galaxy and its central black hole are closely linked. Astronomers can also study black holes through the effects of their immense gravity. One fascinating phenomenon is gravitational lensing, in which the intense gravity of a massive object bends the path of light, much like an optical lens bends rays of light on Earth. Weak gravitational lensing deflects light by tiny angles, while microlensing occurs when the sources are too small to resolve, producing a subtle but detectable brightening. Around the turn of the millennium, the first 3 candidate black holes were discovered using microlensing, and in January of 2022, astronomers announced the first confirmed detection of a microlensing event caused by an isolated black hole. Another way to detect a black hole is by watching stars orbit around it. By carefully tracking their motion, astronomers can infer the presence and mass of the unseen object. Several promising candidates for this type of observation exist around the supermassive black hole at the center of our own Milky Way, known as Sagittarius A. While there is strong evidence supporting the existence of supermassive black holes, the way scientists identify smaller, stellar mass black holes relies on an assumption about the maximum mass a neutron star can have. In other words, if an object in space is observed to be heavier than this maximum limit, it is assumed to be a black hole. But the truth is, the behavior of extremely dense matter is still very mysterious. There may be exotic forms of matter we have not yet discovered that could create other kinds of incredibly dense, massive objects. For instance, some theories suggest that at extremely high densities, matter could exist as free quarks, potentially forming what are called quark stars. Other advanced models in physics propose the existence of Q stars, which arise from certain supersymmetric theories. Even more speculative ideas suggest that quarks and leptons might themselves be made of smaller particles called preons, and in this case, preon stars could exist. These hypothetical objects might help explain some observations of what we currently call stellar black hole candidates. However, even in these theories, general relativity shows that there would still be a maximum possible mass for such objects. Interestingly, the average density of a black hole inside its Schwarzschild radius, essentially the size of the black hole, is inversely proportional to the square of its mass. This means that supermassive black holes are actually much less dense than their smaller stellar mass cousins. For example, a black hole with a mass of 100 million times that of our Sun would have an average density roughly similar to that of water. Because of this, scientists have a better understanding of how matter behaves when forming a supermassive black hole, and alternative explanations for these objects tend to be far simpler. One such alternative might be a massive cluster of very dark objects, but these clusters generally cannot remain stable long enough to account for the observations of supermassive black holes. Over the years, physicists have proposed a few exotic theoretical objects that could mimic black holes almost perfectly, but operate by different physical mechanisms. These include the gravastar, the black star, the nest star, and the dark energy star. Each of these is fascinating in its own right, but none have been confirmed in reality. In 1971, Stephen Hawking demonstrated that under general conditions, the total area of the event horizons of any group of classical black holes can never shrink, even if the black holes collide and merge. This discovery became known as the second law of black hole mechanics, and strikingly resembles the second law of thermodynamics, which states that the total disorder, or entropy, of an isolated system can never decrease. Initially, scientists assumed black holes had zero entropy, just as objects at absolute zero temperature do, but this would violate the second law of thermodynamics because any matter carrying entropy that falls into a black hole would decrease the total entropy of the universe. To resolve this, Jacob Bekenstein proposed that black holes should have entropy proportional to the area of their event horizon. This connection between black holes and thermodynamics was strengthened further in 1974, when Hawking discovered that black holes, according to quantum field theory, emit radiation, now called Hawking radiation, like a glowing black body at a certain temperature. This seems strange because the black hole loses energy as it radiates, shrinking in size. The radiation also carries away entropy, but calculations show that the sum of the entropy of the surrounding matter plus 1/4 of the black hole's horizon area, measured in Planck units, always increases. This allowed scientists to formulate the first law of black hole mechanics as a mirror of the first law of thermodynamics, where the black hole's mass plays the role of energy, its surface gravity acts as temperature, and its horizon area represents entropy. One puzzling feature is that a black hole's entropy depends on its surface area rather than its volume, whereas normally entropy scales with volume. This strange property inspired the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, which suggests that everything happening inside a volume of space can be described by information on the boundary of that volume. While general relativity allows for a semi-classical calculation of black hole entropy, this is still theoretically unsatisfying. In statistical mechanics, entropy is understood as a count of the microscopic arrangements that a system can have while appearing the same on a larger scale. Without a full theory of quantum gravity, we cannot calculate this for black holes in a completely satisfactory way. Some progress has been made. In 1995, Andrew Strominger and Kumran Vafa showed that counting the microstates of a specific supersymmetric black hole in string theory matched the Bekenstein-Hawking entropy. Since then, similar results have appeared for different black holes in both string theory and other quantum gravity approaches, such as loop quantum gravity. Because black holes can be described by only a few basic properties, mass, electric charge, and spin, most information about the matter that formed them seems to vanish. As long as black holes were thought to exist forever, this information loss was not a huge problem. It could be considered locked away inside the black hole and represented on the event horizon according to the holographic principle. However, black holes gradually evaporate through Hawking radiation, which does not seem to carry information about the original matter. This raises the troubling question of whether the information is lost forever, a problem known as the black hole information paradox. This paradox has split the theoretical physics community. In quantum mechanics, losing information would break a fundamental principle called unitarity, and some have argued that breaking unitarity could even violate energy conservation, though this remains debated. In recent years, evidence has grown suggesting that information is indeed preserved when quantum gravity is fully taken into account. One proposed solution to the information paradox is black hole complementarity. In 2012, the firewall paradox was introduced, showing that complementarity might fail. According to quantum field theory in curved spacetime, each emission of Hawking radiation involves two entangled particles. One escapes as radiation, while the other falls into the black hole. If a black hole formed a finite time ago and will evaporate in finite time, then the outgoing particle must eventually become entangled with all previous Hawking radiation. This creates a puzzle because quantum mechanics prohibits a particle from being fully entangled with two independent systems simultaneously. Yet here, the outgoing particle seems entangled both with the infalling particle and with the earlier radiation. To resolve this, physicists may eventually need to give up one of three long-standing principles: Einstein's equivalence principle, unitarity, or the rules of local quantum field theory. One proposed solution, which breaks the equivalence principle, is that a firewall could destroy particles at the event horizon. As of now, which of these principles, if any, might be sacrificed remains an open question, keeping black holes at the frontier of physics as both mysterious and profoundly fascinating objects. Imagine standing on the surface of a planet looking up at the sky, feeling the gentle tug that keeps your feet firmly planted on the ground. That invisible tug, so natural that we hardly think about it, is gravity. Gravity is everywhere. It is the unseen force that orchestrates the motion of planets, moons, stars, and even light itself. It pulls objects toward the center of mass of a body, whether that body is a planet, a star, or something far stranger and denser, like a black hole. A gravity well is a way to visualize this pull, this force of gravity, and it is perhaps one of the most fascinating and elegant concepts in the universe. You can think of a gravity well as a kind of cosmic funnel, an invisible pit that objects naturally fall into. The deeper and steeper the well, the stronger the pull. It is easy to imagine falling into a hole and being unable to climb out. That intuitive idea is what has led mythology and popular culture to refer to any large hole as a gravity well. But the science behind it is far more precise, far more beautiful, and far more complex. Gravity wells are not simply holes, they are curved regions of space-time shaped by mass and energy, forming a natural funnel that becomes steeper the closer you get to the massive object at its center. One of the most popular ways to picture this is to imagine space itself as a stretched fabric, like a vast, invisible trampoline or a delicate mesh. When you place a planet on this fabric, its weight sinks into the surface, stretching and bending it. The heavier the planet, the more the fabric sags. Around this dip, the fabric forms a funnel, gently sloping at first, then curving more steeply as it approaches the center. Place a small ball on the fabric, and it will roll toward the low point in the middle. The closer it gets, the faster it moves, drawn inexorably into the central depression. This simple analogy captures the essence of a gravity well. The closer you are to the massive object, the stronger the gravitational force pulling you inward. Now, let's try a small experiment in your mind, or even at home. Take a thin sheet of rubber, cellophane, or nylon and stretch it tightly over a bowl. Then place a heavy object such as a large marble or a small weight in the center. The material will dip under the weight, forming a concave surface. Now, roll smaller objects like coins or marbles onto the sheet. They will spiral slowly toward the center, accelerating as they approach it, drawn by the curvature of the material. That dip in the sheet represents a gravity well, and the way the coins move toward the center mimics how objects move under the influence of gravity. The center of the well, the point directly under the heavy object, is the deepest and exerts the greatest pull. This visual and tactile analogy helps us grasp a key principle. The strength of a gravity well depends on the mass of the object creating it. A small moon or an asteroid forms a shallow well. A planet like Earth creates a significantly deeper well, and a star like our Sun forms a vast and powerful well, extending its influence far into space. The larger the mass, the deeper the well, and the stronger the gravitational pull. Although we experience Earth's gravity every moment of our lives, it is only a small glimpse of the cosmic scale of these forces. When an apple falls from a tree, we marvel at its descent, yet we are witnessing only a tiny portion of the Earth's gravitational influence. Gravity does not stop at the surface. It reaches far into space, affecting satellites, space stations, the moon, and even distant comets passing through our solar system. To escape Earth's gravitational pull entirely requires enormous energy, as demonstrated every time a rocket or space shuttle launches into orbit. This energy is precisely what scientists call escape velocity, the speed an object must reach to break free from a planet's gravity without further propulsion. For Earth, this speed is roughly 7 miles per second, which is nearly 25,000 miles per hour. Only by reaching this velocity can a spacecraft leave the gravity well behind and venture into the emptiness of space. Our everyday experience of gravity wells can even be made playful. Imagine a spiral wishing well, designed with the shape of a perfect gravity funnel. As objects move down the spiral, they are pulled toward the center, the point of deepest gravity. Yet, with a little clever motion, like spinning a toy called a vortex in a circular motion, coins or small objects can climb back up the walls of the well. This demonstrates an important principle. Gravity can be countered by the right combination of energy and motion. Even though a gravity well draws objects inward, energy can allow objects to resist or escape the pull. At the extreme end of the spectrum lie the most mysterious and powerful gravity wells in the universe: black holes. A black hole is a region of space where the gravity is so strong that nothing can escape, not even light itself. This is why black holes appear black. Without light escaping, they are invisible to our eyes. Their gravity wells are essentially bottomless pits in the fabric of space-time. To leave a black hole once inside its boundary, called the event horizon, would require moving faster than the speed of light, which, according to current physics, is impossible. While this may sound like science fiction, black holes are very real, and we can observe their influence on nearby stars, gas, and even entire galaxies. Many people have drawn playful analogies between gravity wells and other forms of consumption or absorption. For example, some satirists have likened government budgets to black holes, pulling in money relentlessly. However, unlike a black hole, funds in well-managed systems can be directed to beneficial ends, such as charity, research, or infrastructure. While the imagery is similar, a central point drawing everything toward it, the outcomes can differ. Returning to Earth, gravity is what keeps us grounded. Without it, we would float aimlessly into the sky, unable to perform simple acts such as walking, sitting, or dropping objects. Every jump, throw, or swing of a bat is a contest against gravity. In sports, athletes constantly work against this force. A baseball player hitting a soaring home run exerts enormous energy to overcome gravity's constant pull on the ball. A basketball player leaping toward the hoop fights gravity for every inch of vertical height. The stronger the athlete, the more they can resist the pull of gravity temporarily, but gravity is always present, immutable and universal. Gravity is not just resistance against motion, it is a shaping force for motion. It dictates the arc of a thrown ball, the orbit of the moon around Earth, and the trajectory of distant comets moving through the solar system. It is the unseen hand guiding planets around stars, stars around galaxies, and galaxies through the cosmic web. Without gravity, matter would float aimlessly in space, and the structures we see in the universe, planets, stars, galaxies, would never have formed. Understanding the scale of gravitational influence requires considering extreme speeds. On Earth at sea level, sound travels at roughly 769.5 miles per hour, depending on atmospheric conditions. Jets can easily surpass this speed, creating sonic booms as they break the sound barrier. Yet, just as gravity resists the motion of physical objects, it also affects the speed of light, although in more subtle ways. Light travels at an astonishing 186,282 miles per second, which is equivalent to 670,616,629 miles per hour. It covers roughly 1 foot every nanosecond, a rate of travel so immense that it is difficult to comprehend. Even at these incredible speeds, gravity can bend light, slow it slightly, and warp its path across the universe, as seen in gravitational lensing. Consider the journey of light from the Earth to the Moon. The Moon is approximately 238,900 miles away. At the speed of light, this distance is crossed in just over 1 second, roughly 1.3 seconds. If Earth's gravity were weaker, light would arrive slightly faster. If stronger, slightly slower. This simple fact illustrates the profound effect of gravity on all motion, even something as seemingly untouchable as light itself. As we move further into space, the scale of gravity wells becomes even more dramatic. Some planets, stars, and galaxies have gravitational forces so immense that even light cannot escape them. These are the black holes, the ultimate gravity wells. Their pull is absolute. The closer you approach, the steeper the funnel becomes, the stronger the attraction, until you cross a point from which escape is impossible. For all practical purposes, these black holes are cosmic traps, invisible yet detectable through their effects on surrounding matter and radiation. Yet gravity is not merely a destructive force, it is also a creative one. Gravity pulls gas and dust together to form stars. It guides planets into stable orbits, allowing life to develop over billions of years. It shapes the spiral arms of galaxies, the orbits of moons, and the paths of comets. Without gravity, there would be no planets to walk on, no oceans to swim in, no air to breathe, and no stars to light the night sky. Even within our own solar system, gravity wells vary dramatically. The Sun, the massive heart of our solar system, creates a gravity well so deep that all planets orbit it in elegant, predictable paths. Earth's gravity well, though smaller, is still strong enough to keep the Moon in orbit and satellites circling for decades. Mars, with only about a tenth of Earth's gravitational pull, has a shallower well, meaning rockets require less energy to escape its surface. Asteroids, small moons, and dwarf planets have almost negligible wells by comparison, making their gravitational influence extremely weak. The interplay between gravity and energy is particularly important in space travel. Rockets must overcome the pull of Earth's gravity well to reach orbit. This requires immense energy and precise calculations, considering the planet's mass, the desired trajectory, and the velocity needed to escape. Even with modern technology, leaving a planet's gravity well is a remarkable achievement. Space agencies around the world have mastered this art, sending probes to distant planets, launching astronauts into orbit, and studying the cosmos beyond our solar system. Each mission is a demonstration of how we can harness energy to overcome the natural pull of gravity wells. Gravity wells are not static. They can change depending on the distribution of mass. A shifting star, a colliding galaxy, or even the accumulation of dark matter can alter the shape and depth of a gravity well. The universe is alive with movement, and gravity is the silent conductor, guiding the dance of matter and energy. Even on a cosmic scale, this principle holds true. The more massive the object, the deeper and more influential its gravity well. At the cosmic extreme, black holes are the ultimate expression of gravity wells. They are formed when massive stars collapse under their own weight, compressing matter into an infinitesimally small point known as a singularity. Around this singularity is the event horizon, the boundary beyond which nothing can return. The gravity well of a black hole is so steep and so deep that space and time themselves are warped near it. Time slows, light bends, and the very fabric of reality contorts in response to the extreme mass concentrated in such a small volume. Even though we cannot see black holes directly, we can observe their effects. Stars orbiting invisible points, glowing gas spiraling into darkness, and gravitational waves rippling through space are all signatures of these extraordinary gravity wells. They are both terrifying and beautiful, representing the extremes of nature's power. A black hole is, in essence, a gravity well taken to its ultimate conclusion, a place where the pull of gravity is absolute, where the laws of physics as we know them are stretched to the limit, and where the mysteries of the universe seem to converge. In the vastness of our Milky Way galaxy, at the very heart of its swirling stars, dust and gas, lies a mysterious and powerful object whose presence has fascinated astronomers and challenged the limits of human understanding for decades. This object, invisible to ordinary eyes yet exerting a gravitational pull so immense that nothing, not even light, can escape it, is known as Sagittarius A star. Often simply called Sgr A star, this supermassive black hole sits at the very centre of our galaxy, quietly shaping the motions of countless stars around it, like a hidden puppeteer pulling the strings of a celestial dance. While black holes themselves cannot be observed directly because they emit no light, their presence can be inferred by watching how the stars and gas clouds move under their influence. Among these stars, one stands out above all others, for the precision and clarity with which it reveals the presence of this galactic beast. This star is known as S2, or in some astronomical records S0-2, and it has become the crown jewel of evidence for the existence of the supermassive black hole at the centre of the Milky Way. S2 is not a star that can be easily seen from Earth with the naked eye. It is located in the very crowded region near the galactic centre, a place dense with stars, gas clouds and dust, which makes direct observation extremely difficult. To study this star, astronomers had to employ some of the most advanced telescopes in the world, including adaptive optics systems that can correct for the distortions caused by Earth's atmosphere. These sophisticated instruments, mounted on ground-based observatories such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii, allowed scientists to track the precise motion of S2 over many years, measuring its position with incredible accuracy. Each year, each month, and each day of observation added more pieces to a cosmic puzzle, slowly revealing the true nature of the forces at work at the galactic core. The journey to understanding S2 and its orbit around Sagittarius A star began in the early 1990s, when teams of astronomers first noticed a cluster of stars moving at extremely high speeds near the galaxy's centre. Among these, S2 stood out because it follows a highly elliptical orbit that brings it perilously close to the invisible central mass. Its orbit is unlike that of ordinary stars in the galaxy, which usually move in relatively gentle circular paths around the galactic centre. Instead, S2 swings in from a distant point far from the black hole to a closest approach, or pericenter, that takes it extremely close to the unseen monster, before slingshotting back out to a far point in a regular repeated pattern. This orbital motion provides one of the clearest pieces of evidence that the unseen object at the centre is indeed a supermassive black hole. The orbit of S2 has been measured with extraordinary precision. It completes a full orbit around Sagittarius A star approximately every 16.0518 years, a figure determined after decades of meticulous observation. Its path forms an elongated ellipse with a semi-major axis, the average distance from the black hole, measuring roughly 970 astronomical units. To give a sense of scale, 1 astronomical unit, or AU, is the distance between the Earth and the Sun, which is about 150 million kilometres, or roughly 93 million miles. Therefore, the semi-major axis of S2's orbit is nearly 1,000 times the distance from the Earth to the Sun. But what is truly astonishing is how close it comes to the black hole at its closest approach. At pericenter, S2 comes within about 17 light hours of the black hole, which is approximately 18 trillion meters, or nearly 120 astronomical units. At this distance, the gravitational pull of the black hole is so strong that S2 reaches speeds of up to 7,600 kilometers per second, or roughly 2.5% of the speed of light. This speed is far beyond anything experienced in our solar system and reflects the immense gravitational energy concentrated at the galactic center. The observations of S2 have been a triumph of modern astronomy. By carefully plotting its motion over decades, scientists have been able to calculate not only the mass of the central object, but also to confirm its extreme compactness. The mass of Sagittarius A star, the invisible anchor of S2's orbit, is estimated to be around 4 million times the mass of our Sun. Yet this mass is concentrated within a space so small that it could fit inside a sphere with a radius less than the distance between the Sun and Mercury, the innermost planet of our solar system. The combination of enormous mass and extreme compactness leaves no other plausible explanation. The object must be a supermassive black hole, a singularity predicted by Einstein's general theory of relativity. No star cluster, no dense cloud of ordinary matter could be packed into such a tiny volume without collapsing into a black hole. The importance of S2's orbit extends beyond proving the existence of a supermassive black hole. Its motion also provides a unique laboratory for testing the predictions of general relativity under extreme gravitational conditions. When S2 approaches the pericenter of its orbit, it moves through a region of space-time so intensely curved by gravity that relativistic effects become measurable. One such effect is the precession of the orbit, where the ellipse of the star's path gradually rotates over time due to the warping of space-time by the black hole's mass. This effect is similar in principle to the precession of Mercury's orbit around the Sun, which was famously explained by Einstein over a century ago, but in the case of S2, the effect is vastly larger due to the extreme gravitational environment. In 2017 and 2018, astronomers observed S2 making its closest approach and detected the predicted relativistic redshift in its light. This shift occurs because the immense gravity of the black hole stretches the wavelength of the light coming from the star, making it appear redder than it would in weaker gravitational fields. The agreement between observation and theory provided one of the most dramatic confirmations of general relativity in action, far beyond anything possible in the solar system. Tracking S2 has not been easy. The region around Sagittarius A star is shrouded in interstellar dust that blocks visible light, so astronomers rely on infrared observations to peer through the obscuring clouds. Even with infrared telescopes, resolving individual stars in the dense cluster requires the highest spatial resolution achievable from Earth. Adaptive optics technology, which compensates for atmospheric turbulence in real time, has been critical in this effort. Without it, the motions of S2 and its neighbouring stars would be smeared into an indistinct blur, hiding the delicate details that reveal the gravitational influence of the central black hole. In addition, the observations must be repeated year after year, decade after decade, to measure the star's full orbit and detect the subtle, relativistic effects. This long-term commitment has required not only technological innovation, but also patience and persistence on the part of astronomers. Beyond its role as a proof of the black hole, S2 offers insights into the environment near the galactic centre. The star is relatively young, only a few million years old, which is surprising given the hostile conditions near the black hole. The intense gravitational forces, strong radiation fields, and frequent close encounters with other stars make the formation and survival of young stars near the centre a challenging problem for astrophysicists. Understanding how S2 came to exist in such a region helps scientists study the complex dynamics of star formation, migration, and interaction in extreme gravitational environments. Some theories suggest that stars like S2 may have formed further out in the galaxy and migrated inward, while others propose that star formation can occur even close to the black hole under certain conditions. Observing S2 in detail provides clues that help distinguish between these scenarios. S2 also interacts with the broader population of stars near Sagittarius A star, known as the S-star cluster. This cluster contains dozens of stars moving in various orbits around the black hole, but S2 is among the most closely studied because of its well-defined orbit and short orbital period relative to other stars in the cluster. The motions of these stars collectively allow astronomers to map the gravitational potential near the black hole, estimate its mass distribution, and detect any deviations from simple models. In some cases, careful analysis of these stellar motions has been used to search for additional massive objects near the centre, including possible intermediate mass black holes or concentrations of dark matter. S2's precise orbit serves as a reference point in these studies, anchoring our understanding of the dynamics in one of the most extreme regions of the Milky Way. The discovery and monitoring of S2 has been a story of international collaboration and technological ingenuity. Teams from institutions in Germany, the United States, Chile, and other countries have worked together, pooling their expertise and resources to carry out long-term observational campaigns. The German team, led by Reinhard Genzel, and the American team, led by Andrea Ghez, independently tracked S2 and other stars near the galactic centre, eventually converging on similar measurements that confirmed the presence of a supermassive black hole. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for their work, highlighting the global significance of these discoveries and the extraordinary effort required to uncover the secrets of the Milky Way's core. One of the most remarkable aspects of S2's story is the way it transforms the abstract concept of a black hole into something tangible and measurable. For many years, black holes existed only in the realm of theoretical physics, predicted by the equations of general relativity but without direct observational proof. The motions of S2 and its companions provide a direct window into this otherwise invisible world. By watching S2 swing around the galactic centre at breathtaking speeds, astronomers can see the effects of the black hole, measure its mass, and confirm its compactness. Each data point, each image captured in the infrared, and each spectroscopic measurement adds to a growing picture of the black hole and the extreme gravitational landscape surrounding it. S2's case also illustrates the power of patient, precise, and sustained observation in astronomy. The star's orbit spans over 16 years, meaning that a full understanding of its motion requires decades of careful monitoring. Early observations in the 1990s provided hints of its peculiar orbit, but it was only after multiple orbits were tracked that the picture became clear. Each new observation refined the parameters of its orbit, reduced uncertainties in the mass of the black hole, and revealed relativistic effects that were previously undetectable. In this way, S2 serves as a testament to the long-term vision and dedication of the astronomical community, showing that some of the universe's deepest secrets can only be uncovered through patience and persistence. Moreover, S2's story highlights the interplay between theory and observation in modern science. General relativity predicted the existence of black holes and described the effects of extreme gravity on nearby objects, but it was observations of stars like S2 that provided the concrete evidence needed to confirm these predictions. The precise measurement of S2's orbit, its speed at pericenter, and the relativistic redshift of its light all match the predictions of Einstein's equations to remarkable accuracy. This alignment between theory and observation strengthens our confidence in the underlying laws of physics and demonstrates that even in the extreme environment of a supermassive black hole, the universe behaves in a predictable and comprehensible way. In addition to its scientific significance, S2 captures the imagination in a more human sense. It is easy to picture this lone star hurtling around an invisible monster, swinging close to a region from which nothing can escape, moving faster than anything we can experience in our daily lives. The fact that we can detect its motion, measure its speed, and use it to probe the most extreme gravitational environment in our galaxy is a triumph of human curiosity and ingenuity. S2 embodies the intersection of natural wonder, scientific rigor, and technological achievement, standing as both a tool for discovery and an object of awe. Finally, the case of S2 is not the end of the story. It is a beginning. Ongoing and future observations will continue to refine our understanding of the galactic center, probe the behavior of matter and light near a supermassive black hole, and test the limits of general relativity. Projects such as the Extremely Large Telescope, scheduled to begin operations in the next decade, will allow even more precise tracking of S2 and other stars in the cluster. In combination with advances in infrared and radio astronomy, these observations may reveal additional surprises such as previously unseen stars, compact objects, or even faint signs of accretion events around the black hole. Each orbit of S2 brings new opportunities to learn, to test, and to marvel at the powerful forces that govern our galaxy. In the heart of our Milky Way galaxy, lurking silently, there exists a colossal and mysterious presence, one so powerful that even light, the fastest traveller in the universe, cannot escape its grasp. This is Sagittarius A, the supermassive black hole that reigns over the centre of our galaxy. For a long time, it was a silent giant, a sleeping monster, almost imperceptible against the backdrop of stars and cosmic dust that surrounds it. Yet, despite its stillness, astronomers and astrophysicists knew that it was far from dormant. Occasionally, like a slumbering beast stirred by unseen forces, it would awaken, sending out bursts of energy in the form of X-rays, sudden flashes that ripple through the cosmos. These phenomena are known as X-ray flares, and they are some of the most captivating yet puzzling signs of activity from one of the most enigmatic objects in the universe. X-ray flares are like cosmic fireworks, brief, brilliant, and unpredictable. To imagine them, picture a vast dark ocean, calm and silent under a moonless sky, and then imagine the sea suddenly exploding with brilliant shimmering light that lasts only for a short moment. That is what a black hole flare resembles, though it is unimaginably more powerful than any explosion on Earth. These bursts are the result of matter falling into the black hole, a process that is both violent and chaotic. In a black hole's immediate vicinity, gravity is so intense that it stretches and tears objects apart, a process scientists call spaghettification. Gas, dust, and even whole stars that stray too close are pulled toward the black hole, forming what is known as an accretion disc, a swirling, spiraling maelstrom of matter, moving at nearly the speed of light. Within this disk, friction and gravitational forces heat the material to millions of degrees, producing radiation that can be detected by telescopes tuned to X-ray frequencies. Yet, these X-ray flares are not constant. Sagittarius A does not shine brightly all the time. Instead, it alternates between periods of relative quiet and sudden eruptions. These flares occur unpredictably, sometimes separated by hours, sometimes days, and occasionally they can last for only a few minutes. Scientists have observed these flares since the 1990s, using instruments aboard satellites such as the Chandra X-ray Observatory, launched in the year 1999, and the XMM Newton, launched in 2000. These observatories orbit far above Earth's atmosphere, which blocks X-rays from space, allowing astronomers to catch the fleeting flashes of energy that would otherwise be invisible. Each flare provides a unique glimpse into the turbulent environment near the black hole, offering clues about the forces at work in a region where the laws of physics are pushed to their extreme. The most powerful flares recorded from Sagittarius A can reach luminosities of up to 100 times greater than the black hole's normal X-ray emission. To put this into perspective, the energy released in one such flare in just a few minutes can equal what our Sun emits over an entire day. Despite this immense energy, the flares are still small compared to the violent outbursts observed from other, more active galactic nuclei. Sagittarius A is relatively quiescent, which is why these occasional flares stand out so dramatically against its normally faint emission. Scientists are fascinated by these bursts because they may reveal not only the black hole's behaviour, but also the extreme physics of matter under conditions that cannot be replicated on Earth. The causes of X-ray flares are still a subject of active research, with several theories attempting to explain them. One of the leading ideas is that these flares are caused by sudden magnetic reconnection events. In the accretion discs surrounding the black hole, magnetic fields are twisted and tangled by the motion of the hot ionized gas. Occasionally, these fields snap and realign, releasing enormous amounts of energy in the process, much like solar flares on our own sun, but magnified many billions of times. These events can accelerate particles to near-light speeds, producing X-rays as the particles collide with surrounding matter or spiral along magnetic field lines. Another possibility is that the flares result from clumps of gas or small objects, perhaps remnants of asteroids or comets, that wander too close to the black hole. As these objects are torn apart by tidal forces, they heat up and emit bursts of X-rays, briefly illuminating the region around the black hole before disappearing into the abyss. The study of these flares is not just about understanding black holes, it is also a window into the extreme physics that governs our universe. Near a black hole, space and time themselves are stretched and warped. General relativity, Einstein's groundbreaking theory, predicts that the immense gravity of a black hole distorts light and slows time. Observing X-ray flares allows scientists to test these predictions under conditions that cannot be created in a laboratory. For example, the precise timing and energy spectrum of a flare can provide information about the black hole's spin and the structure of the space around it. Some flares even show evidence of quasi-periodic oscillations, tiny rhythmic pulses that hint at orbiting hotspots in the accretion disk, moving at relativistic speeds close to the event horizon, the boundary beyond which nothing can escape. One particularly remarkable observation occurred in the year 2010, when astronomers detected a bright X-ray flare from Sagittarius A that lasted for nearly 120 minutes, the longest such flare ever observed at the time. The flare's intensity was nearly 150 times the black hole's normal emission, briefly making the centre of the galaxy one of the brightest X-ray sources in the sky. Studies of this event suggested that the flare was caused by magnetic activity in the innermost regions of the accretion disk, a region no larger than the orbit of Mercury around our Sun. The observation provided crucial evidence that even a relatively quiet supermassive black hole can produce violent high-energy events that illuminate its surroundings and allow scientists to probe the mysteries of extreme gravity. Beyond the scientific data, X-ray flares also capture the imagination because they remind us of the dynamic and violent universe we inhabit. The centre of the Milky Way, hidden behind dense clouds of gas and dust, is often portrayed as a tranquil and static region. Yet, the occurrence of these flares tells a different story, one of continuous activity and unseen forces at work. Each flare is a signal from a distant giant, a message encoded in bursts of high-energy radiation, travelling tens of thousands of light-years to reach Earth. Studying X-ray flares requires not only sophisticated instruments, but also careful observation strategies. Satellites like Chandra and XMM Newton monitor Sagittarius A for extended periods, often conducting deep, continuous observations lasting several days. This patience is necessary because flares are unpredictable. Astronomers must watch and wait for the black hole to awaken from its slumber. When a flare occurs, instruments record not only the intensity of the X-rays but also their energy spectrum and timing, creating a detailed profile of the event. By comparing multiple flares over time, scientists can look for patterns, correlations, and differences, building a comprehensive picture of the black hole's behavior. In some cases, simultaneous observations are made in other wavelengths, such as infrared or radio waves, providing a multidimensional view of the flare and its effects on the surrounding environment. Infrared observations are particularly valuable because they can reveal the motion of hot gas near the black hole. Some flares observed in X-rays are accompanied by near-infrared emissions, suggesting that the same population of energetic particles is responsible for radiation across multiple wavelengths. Radio observations, on the other hand, can trace the behavior of larger-scale magnetic fields and the movement of matter farther from the event horizon. By combining data from different parts of the electromagnetic spectrum, astronomers can piece together the complex puzzle of how flares originate, how energy is transported, and how the black hole interacts with its immediate surroundings. One of the most intriguing questions about X-ray flares is their potential impact on the broader environment of the Milky Way. While the energy released in a single flare is enormous, the black hole is still relatively distant from most stars in the galaxy, and the bursts do not pose any danger to Earth. However, over cosmic timescales, repeated flaring activity could influence the interstellar medium, the vast clouds of gas and dust between stars, by heating and stirring it. This process could affect the formation of new stars, the distribution of matter near the galactic center, and even the growth of the black hole itself. Understanding these interactions is a key part of modern astrophysics, linking the study of black holes to the evolution of entire galaxies. Another fascinating aspect of X-ray flares is their connection to theoretical predictions and extreme physics. The region near the event horizon is governed by the interplay of gravity, magnetism, and relativistic effects. Particles in this environment experience forces that are incomprehensible in everyday life. They are stretched, twisted, and accelerated to velocities approaching the speed of light. By observing flares, scientists can test models of particle acceleration, magnetic reconnection, and relativistic motion. Some flares may even provide indirect evidence of phenomena predicted by quantum gravity theories, such as the behavior of matter near the singularity, where classical physics breaks down. Each flare is therefore not just an observational curiosity but a natural laboratory for exploring the fundamental laws of the universe. In the year 2015, astronomers witnessed one of the brightest X-ray flares from Sagittarius A in recent history. The flare lasted nearly 2 hours and reached a peak luminosity of several times 10 to the 34 ergs per second, equivalent to what our Sun emits in more than a week. Detailed analysis revealed rapid variations in intensity, suggesting that the emitting region was extremely compact, no larger than a few times the size of the Earth's orbit around the Sun. The event reinforced the idea that magnetic reconnection and small-scale accretion events are likely responsible for the most energetic flares. It also highlighted the incredible precision and sensitivity of the modern X-ray observatories, capable of detecting subtle changes in radiation from a source more than 26,000 light-years away. Despite decades of observations, many mysteries about X-ray flares remain. Scientists continue to debate the exact mechanisms, the role of magnetic fields, the origin of the high-energy particles, and the connection between flares and the long-term growth of the black hole. Some researchers suggest that flares may be triggered by interactions with nearby stars or by infalling clouds of gas, while others propose that the variability is intrinsic to the turbulent accretion disk itself. The challenge is compounded by the fact that Sagittarius A is surrounded by dense gas and dust, which obscure the region in visible light, forcing astronomers to rely on high-energy radiation and advanced imaging techniques to probe its secrets. Future missions promise to shed even more light on these extraordinary events. Satellites such as the European Space Agency's Athena, planned for launch in the mid-2030s, will offer unprecedented sensitivity and spectral resolution in X-rays, allowing scientists to dissect flares in finer detail than ever before. Ground-based observatories equipped with adaptive optics will continue to track the motion of stars and gas near the black hole, providing context for the X-ray activity. By combining these observations, astronomers hope to develop a unified model of how matter behaves in the extreme gravity of a supermassive black hole, how flares are triggered, and what they tell us about the fundamental forces at play in the universe. X-ray flares are more than just bursts of radiation. They are cosmic signals from the edge of a void, messages from a sleeping giant whose presence shapes the Milky Way in profound ways. Each flare illuminates the darkness, revealing the hidden dynamics of matter and energy under the most extreme conditions imaginable. They challenge our understanding of physics, test our technological ingenuity, and inspire wonder about the universe we inhabit. Through patient observation, careful analysis, and bold theoretical exploration, humanity continues to decipher these messages, unlocking secrets that lie at the very heart of our galaxy. In a sense, X-ray flares are the voice of Sagittarius A, the silent monarch of the Milky Way, speaking in bursts of light that traverse tens of thousands of light-years to reach us. The study of X-ray flares has also changed our perspective on what it means for a black hole to be quiet or active. In the past, astronomers believed that only the most luminous and energetic black holes, found in other galaxies as quasars or active galactic nuclei, were capable of dramatic outbursts. Sagittarius A, by contrast, appeared modest and sedate. Yet, the discovery and careful monitoring of its X-ray flares revealed that even a seemingly dormant supermassive black hole harbours the potential for sudden intense activity. These flares are like glimpses of the underlying power hidden beneath the surface, evidence that the black hole is not a static object, but a dynamic, evolving entity, influenced by its surroundings and capable of dramatic bursts of energy when conditions align. Beyond their scientific importance, X-ray flares also serve as a profound reminder of the scale and power of the universe. The energy involved in these flares, the speed at which particles move, and the forces at play are far beyond anything humans experience in daily life. They connect us to the larger cosmos, placing our existence within a vast, dynamic, and often violent universe. Observing these flares is both an intellectual pursuit and a humbling experience. Sagittarius A, often abbreviated as Sgr A, is the supermassive black hole that lies at the very heart of our home galaxy, the Milky Way. This black hole is not only fascinating because of its immense size and mass, but also because it serves as a key point of comparison to countless other black holes scattered across the universe. To understand the uniqueness of Sagittarius A, we first need to explore what black holes are in general, and how they vary in size, mass, and behaviour. Black holes are among the most mysterious and intriguing objects in the cosmos. They are regions in space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. The event horizon is like the invisible boundary of a black hole, beyond which escape is impossible. Anything that ventures too close is trapped forever, pulled into the depths of the black hole. Black holes are classified broadly into three main categories: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes are the smallest type, usually formed when massive stars reach the end of their life cycles and collapse under their own gravity. These black holes typically have masses ranging from about 3 to 20 times the mass of our Sun. Their relatively small size means that they are scattered throughout galaxies and are often discovered when they interact with companion stars, forming systems known as X-ray binaries. These systems are of great interest to astronomers because the radiation emitted as matter falls into the black hole allows us to detect these otherwise invisible objects. Intermediate mass black holes, as the name suggests, are larger than stellar mass black holes but smaller than the supermassive ones. Their existence has been hypothesized for decades, but only in recent years have astronomers begun to gather substantial evidence of their presence. They are thought to have masses ranging from a few hundred to a few 100,000 times the mass of the Sun. Despite their size, they remain elusive because they are rare and difficult to detect. Some may lurk at the centres of smaller galaxies or in dense clusters of stars, quietly pulling in matter without attracting much attention. Supermassive black holes are the giants among black holes, with masses ranging from hundreds of thousands to billions of times the mass of our Sun. Sagittarius A is one such supermassive black hole, and it holds the record as the central anchor of the Milky Way. Astronomers estimate its mass to be about 4 million times the mass of the Sun. To put this into perspective, Imagine the combined mass of 4 million suns compressed into a space smaller than our solar system. The density and gravitational pull at its centre are so extreme that they warp space and time around it. The surrounding stars and gas clouds orbit this invisible giant, moving at tremendous speeds due to its overwhelming gravity. Observing these stellar motions has been one of the most compelling pieces of evidence for the existence of Sagittarius A. Compared to other supermassive black holes, Sagittarius A is somewhat modest. For instance, the supermassive black hole at the centre of the galaxy known as M87, famously imaged by the Event Horizon Telescope in the year 2019, has a mass of about 6.5 billion times that of the Sun. This means it is over 1,000 times more massive than Sagittarius A. Despite being so much larger, M87's black hole is located much farther away, approximately 53 million light-years from Earth. In contrast, Sagittarius A is relatively close, only about 26,000 light-years away, making it far easier to study in detail. Its proximity allows astronomers to track individual stars orbiting around it, like the star known as S2, which completes an orbit roughly every 16 years. Watching S2 speed past the black hole at pericenter, reaching velocities of around 25 million kilometers per hour, has allowed scientists to test Einstein's theory of general relativity in the extreme gravitational environment near a supermassive black hole. The behaviour of Sagittarius A also differs from that of more active supermassive black holes. Many galaxies host black holes that are actively feeding, consuming enormous amounts of gas and dust, and emitting brilliant radiation across the electromagnetic spectrum, particularly in X-rays and radio waves. These are known as active galactic nuclei. Sagittarius A, by contrast, is relatively quiet. It is classified as a low-luminosity black hole, meaning it accretes matter at a very slow rate. This quiet nature may be one reason why life on Earth has been able to exist in a relatively stable environment for billions of years, shielded from the intense radiation that more voracious black holes produce. Occasionally, Sagittarius A exhibits small bursts of X-ray flares, which astronomers interpret as the swallowing of small amounts of gas, or the close approach of stars and smaller objects. These flares provide valuable insight into the dynamics near the event horizon, helping scientists refine their understanding of black hole physics. When comparing Sagittarius A to stellar mass black holes, the differences are even more striking. Stellar mass black holes, with their comparatively tiny gravitational reach, have event horizons only a few tens of kilometers across. Sagittarius A, on the other hand, has an event horizon roughly 12 million kilometers in diameter, wide enough to encompass the orbit of Mercury several times over. The vast difference in scale highlights the diversity of black holes, which, despite following the same fundamental physical laws, display a breathtaking range of characteristics depending on their mass and environment. Observational techniques also differ depending on the type of black hole. Stellar mass black holes are often studied through X-ray emissions from accretion discs, or by observing the gravitational influence on nearby stars. Supermassive black holes like Sagittarius A require different approaches. One of the most remarkable achievements in recent years has been the use of very long baseline interferometry, a technique that links multiple radio telescopes around the world to create a virtual telescope the size of the Earth itself. This method has allowed astronomers to achieve unprecedented resolution, capable of imaging the shadow of a black hole. While Sagittarius A's shadow has proven more challenging to capture than M87's, due to its rapid variability and smaller size relative to the Earth's angular resolution, progress continues as technology improves and observational techniques become more refined. Another aspect that sets Sagittarius A apart is its environment. Unlike M87, which resides in a massive elliptical galaxy with a densely packed stellar population and abundant interstellar gas, the Milky Way is a barred spiral galaxy with a more moderate star density around its centre. This means that Sagittarius A has a less dramatic feeding environment, with fewer opportunities for rapid growth compared to some of the most luminous black holes in the universe. Nevertheless, it plays a critical role in shaping the dynamics of the central star cluster, influencing the motion of stars and the distribution of gas in the innermost region of our galaxy. The study of Sagittarius A also offers insight into the evolution of galaxies themselves. Astronomers believe that nearly every galaxy hosts a supermassive black hole at its centre, and that these black holes and their host galaxies evolved together. By understanding Sagittarius A, scientists can learn about the Milky Way's past and make inferences about how supermassive black holes grow over cosmic time. Sagittarius A appears to have grown relatively slowly, at least in its current state, suggesting a history of intermittent feeding rather than continuous voracious consumption. Comparing this with more massive and active black holes helps build a complete picture of galactic evolution, highlighting the complex interplay between black holes and their environments. Sagittarius A also provides a laboratory for testing the limits of physics. The extreme gravity near the black hole's event horizon bends space and time in ways that cannot be reproduced on Earth. Observations of stars and gas clouds near Sagittarius A have confirmed predictions of general relativity, including the precession of orbits and gravitational redshift, where light escaping the black hole's influence loses energy and shifts toward longer wavelengths. These phenomena, observed in real time, offer one of the best opportunities to study how matter and light behave under the most intense gravitational forces imaginable. When we compare Sagittarius A with the most extreme supermassive black holes, such as the quasar TON 600, which has a mass estimated to be about 70 billion times that of the Sun, we see a staggering difference. TON 600's black hole is almost 18,000 times more massive than Sagittarius A, highlighting the immense range of sizes that black holes can have. Yet, despite the difference in mass, the underlying physics remains consistent, governed by the same rules of gravity and relativity. This consistency is a testament to the universality of the laws of physics, which apply equally to the smallest stellar mass black holes and the mightiest supermassive giants. Another interesting point of comparison is the rate of rotation, or spin, of black holes. Spin affects the structure of the space-time around a black hole, influencing how matter moves near the event horizon and how jets of high-energy particles are formed. While the exact spin of Sagittarius A is still being studied, evidence suggests that it is not spinning at the extreme rates observed in some other supermassive black holes. In contrast, black holes like those powering quasars often spin rapidly, channeling energy into powerful relativistic jets that can extend across millions of light-years. The quieter spin of Sagittarius A may be another reason it is relatively subdued, without the energetic outflows seen in more extreme galaxies. Sagittarius A serves as a stepping stone for humanity's understanding of black holes and the universe. Being the closest supermassive black hole, it allows astronomers to refine their models, test their instruments, and prepare for the study of more distant and extreme objects. The lessons learned from Sagittarius A inform not only astrophysics, but also cosmology, helping scientists explore fundamental questions about the nature of space, time, and gravity itself. By comparing it to other black holes, both smaller and larger, quiet and active, nearby and distant, we gain a deeper appreciation for the diversity and complexity of these enigmatic objects. Each black hole tells a story about the universe's history, about the life and death of stars, and about the evolution of galaxies over billions of years. Astronomers often describe certain black holes as supermassive, and this label is not just a casual exaggeration but a carefully considered reflection of their staggering size and influence. In the vastness of space, black holes come in a range of sizes, but the ones that earn the title of supermassive are truly in a class of their own. To understand why astronomers use this term, it helps to compare them to more familiar cosmic objects, and to explore the extraordinary scales involved. Ordinary black holes, often called stellar mass black holes, are formed when massive stars reach the end of their life cycles and collapse under their own gravity. These stellar mass black holes typically weigh anywhere from a few times to perhaps a few dozen times the mass of our Sun. Even that is an immense amount of matter compacted into a space so tiny that it would fit well within the span of a small city, and their gravitational pull is so strong that nothing, not even light, can escape once it crosses the black hole's event horizon, the point of no return. However, supermassive black holes are on an entirely different scale, so vastly more enormous that comparing them to stellar mass black holes is almost like comparing a grain of sand to an entire planet. Supermassive black holes can contain millions or even billions of times the mass of our Sun, concentrated in a region whose diameter can stretch across millions of kilometers, and yet in cosmic terms, this is still a relatively small size given the amount of matter packed inside. The term supermassive thus reflects not only their incredible mass, but also their role as titanic gravitational anchors, often residing at the centres of galaxies, including our own Milky Way, where they exert a powerful influence over the motions of countless stars, gas clouds, and other objects. These enormous objects are so massive that their gravitational pull governs the orbits of stars hundreds of light years away, effectively shaping the structure and dynamics of entire galaxies. In comparison, a stellar mass black hole might only tug on nearby stars or gas in its immediate vicinity, but a supermassive black hole can dominate a whole galactic neighbourhood. This disparity in influence is one of the reasons astronomers are compelled to use a special term. Another important factor that contributes to the supermassive designation is the extreme density and compactness of these objects. Despite containing such enormous quantities of matter, supermassive black holes occupy regions that, while large by everyday human standards, are minuscule compared to the galaxies they inhabit. To put this into perspective, consider Sagittarius A, the supermassive black hole at the centre of the Milky Way. It has a mass of about 4 million times that of our Sun, yet its event horizon, the boundary beyond which nothing can escape, has a radius of only about 12 million kilometres, roughly 30 times the distance from the Earth to the Sun. This combination of immense mass and relatively tiny size leads to gravitational fields of astonishing intensity, strong enough to warp space-time itself and influence the paths of light and matter across enormous distances. When astronomers study the motions of stars near these central black holes, they can see the signature of this extreme gravitational pull. For example, the star S2, which orbits Sagittarius A, follows an elongated elliptical path, coming as close as 17 light-hours from the black hole before swinging far out again, completing one orbit approximately every 16 years. Observing such orbits provides irrefutable evidence of a central mass so dense that no ordinary star or collection of stars could account for it, leaving a supermassive black hole as the only viable explanation. Supermassive black holes are not just heavy, they're also the engines of some of the most energetic phenomena in the universe. When matter falls into a supermassive black hole, it forms an accretion disc, a swirling, spiralling mass of gas and dust that heats up to extraordinary temperatures and emits enormous amounts of radiation, often outshining the entire galaxy in which the black hole resides. These active galactic nuclei, or quasars, demonstrate the dramatic power that such supermassive objects wield. The very term supermassive is, in part, a reflection of this capacity to dominate their surroundings both gravitationally and energetically. It is worth noting that the origin of supermassive black holes remains one of the great mysteries of astrophysics. Unlike stellar mass black holes, which are relatively well understood to form from collapsing stars, supermassive black holes likely grow through a combination of mechanisms, including the accretion of vast amounts of gas over millions or billions of years and the merging of smaller black holes. Some evidence suggests that they could have begun forming very early in the universe, within the first few 100 million years after the Big Bang, quickly accumulating mass to become the colossal entities we observe today. This rapid growth challenges our understanding of cosmic evolution and makes supermassive black holes all the more remarkable. Their mass and scale are so extreme that astronomers cannot help but distinguish them with a term that conveys the sheer magnitude of their presence. Additionally, supermassive black holes serve as laboratories for the laws of physics under conditions impossible to reproduce on Earth. They offer insights into the nature of gravity, the behaviour of matter under extreme compression, and even the warping of space-time predicted by Einstein's theory of general relativity. Observations of stars orbiting near these black holes, along with the detection of flares and high-energy emissions from their surroundings, provide a window into these exotic environments. By calling them supermassive, astronomers signal to the scientific community and the public alike that these objects are not ordinary black holes, but are extraordinary in both size and effect, deserving special attention and study. The label also helps differentiate them from other massive objects in space, such as neutron stars which, while incredibly dense, contain only a few times the mass of the Sun, or intermediate mass black holes, which occupy a curious middle ground but are far smaller than their supermassive counterparts. Supermassive black holes are thus placed at the extreme end of the mass spectrum, highlighting their unparalleled dominance in the cosmic hierarchy. In practical terms, the term supermassive also aids astronomers in communication, offering a concise way to describe objects that, by any measure, defy ordinary human comprehension. It conveys both awe and scientific precision, awe at their scale, and precision in the sense that their mass is not merely large but far beyond what is seen in stellar remnants. It is this combination of extraordinary mass, gravitational influence, energetic output, and cosmic significance that justifies the use of the word supermassive rather than any other descriptor. In many ways, the term encapsulates both the measurable and the conceptual aspects of these cosmic titans. Furthermore, studying supermassive black holes informs our understanding of galaxy formation and evolution. Observations indicate that almost every large galaxy hosts a supermassive black hole at its center, suggesting that the growth of galaxies and their central black holes are intimately connected. The relationship between the mass of a supermassive black hole and the properties of its host galaxy, such as the velocity of stars in the galactic bulge, hints at a co-evolutionary process in which galaxies and black holes shape each other over cosmic timescales. In this context, the adjective supermassive also implies a central governing role. These black holes are not merely large by accident, but are fundamental components of the galactic ecosystem, controlling or influencing processes that span tens of thousands of light years. Even when supermassive black holes lie dormant, their mass is enough to affect the motion of stars and gas across a galaxy, maintaining a gravitational order that persists over billions of years. The label supermassive thus captures both their physical enormity and their profound importance in the cosmic landscape. Moreover, the use of this term reflects a comparative perspective, a way for astronomers to categorize and differentiate among black holes based on their mass. While the physics of a black hole does not fundamentally change with size, every black hole has an event horizon and a singularity, their consequences for surrounding matter and their detectability vary dramatically with scale. Stellar mass black holes, though extreme, are often invisible unless they interact with nearby matter. Supermassive black holes, by contrast, can dominate entire galactic centers and become observable across vast cosmic distances due to the radiation emitted from their accretion discs. The word supermassive therefore conveys not only raw numbers, but also the scale of their impact, the range of their influence, and their observational prominence. In addition to these scientific reasons, the term also helps capture the imagination of the public. When astronomers announce the discovery of a supermassive black hole or measure its mass, the word immediately conveys a sense of wonder and scale, helping people conceptualize an object that is otherwise almost impossible to grasp. It emphasizes that these are not just big black holes, but entities of almost inconceivable magnitude, holding millions to billions of suns worth of mass within a comparatively tiny volume, and shaping the cosmos on a galactic scale. In sum, astronomers call certain black holes supermassive because of a combination of factors that together justify the term. These include their incredible mass, which can reach millions or billions of times that of our Sun, their immense gravitational pull, which dominates the motion of stars and gas across entire galaxies, their energetic potential, which powers some of the brightest and most extreme phenomena in the universe, their fundamental role in galactic formation and evolution, and the challenge they present to our understanding of physics and cosmic history. The label succinctly communicates both their quantitative properties and their qualitative significance, distinguishing them from smaller black holes and other cosmic objects. By using the word supermassive, astronomers convey the awe-inspiring scale of these cosmic giants, their central importance in galaxies, and their capacity to teach us about the universe in ways that no other objects can. They are not merely large, they are supermassive, true titans of the cosmos, whose very existence stretches the imagination and tests the limits of our understanding. Through observation, measurement, and comparison with other celestial bodies, scientists continue to explore why these black holes are supermassive, how they grow, and what their presence tells us about the formation and evolution of galaxies, including our own. Each new discovery, each orbit mapped, each flare observed, adds to a picture of the universe in which these supermassive black holes are both central characters and guiding forces, shaping the cosmos on a scale that is almost beyond human comprehension. yet essential for understanding the universe as a whole. Their mass, influence and power are such that no other label could adequately describe them, and so astronomers rightly and deliberately call them supermassive. When astronomers speak about black holes, they're often describing objects so strange, so extreme, and so powerful that they defy ordinary human understanding. Among these cosmic enigmas, there is one particularly awe-inspiring category: the supermassive black holes. These are not ordinary black holes, the kind formed when a massive star collapses at the end of its life. No, supermassive black holes occupy an entirely different scale of magnitude. They are behemoths of the universe, objects so dense and so massive that their very existence seems almost unbelievable. One of the most astonishing facts about these celestial monsters is the sheer mass they contain within a single point. Imagine, if you can, the mass of 4 million suns. Yes, 4 million stars, each as bright, as enormous and as hot as our own sun, compressed into an area so small that it is essentially a single point in space. This is not science fiction. This is reality, and it exists at the very heart of our galaxy, the Milky Way, in the region astronomers have named Sagittarius A star, or Sgr A star for short. The concept itself is staggering. To comprehend 4 million times the mass of our Sun in one location, we need to first grasp the scale of our own star. The Sun, a massive ball of gas at the centre of our solar system, contains more than 99% of all the mass in this little neighbourhood of planets, moons, asteroids and comets. It is unimaginably heavy, weighing approximately 1.987 times 10 to the 33rd grams, or about 1 quintillion trillion kilograms. Now multiply that mass by 4 million. The resulting number is beyond ordinary human intuition. It is roughly 7.92 times 10 to the 39 kilograms. This is a quantity of matter that could hardly be visualized, an amount so immense that it bends the very fabric of space and time around it. And yet, all this mass resides in a volume that, by cosmic standards, is almost infinitely small. When we say a single point, we're referring not just to a dot in space, but to a singularity, a location where matter is compressed to an extreme density, and the usual laws of physics as we know them begin to break down. How can something so massive exist in such a tiny space? This question has puzzled astronomers, physicists, and mathematicians for decades. The answer lies in the extraordinary nature of gravity. Gravity, the force that binds planets to stars, stars to galaxies, and galaxies to clusters of galaxies, is the invisible glue of the cosmos. Under ordinary circumstances, gravity pulls matter together but is balanced by other forces, such as thermal pressure or electromagnetic forces, which prevent complete collapse. In the case of stars, for example, gravity tries to pull all the material inward, but the intense heat and pressure generated by nuclear fusion at the star's core push outward, maintaining an equilibrium. However, when a massive enough amount of matter is concentrated into a small enough space, gravity can overwhelm all opposing forces. This is precisely what occurs in a black hole. Once the matter crosses a certain threshold, the gravitational pull becomes so intense that nothing, not light, not radiation, not even the fastest particles in the universe can escape. The result is a black hole, an object of infinite density contained in a point known as a singularity, surrounded by an event horizon, the boundary beyond which escape is impossible. Sagittarius A star at the centre of the Milky Way is a prime example of a supermassive black hole. Astronomers have been studying this mysterious object for decades, observing the motions of stars and gas clouds in the central region of our galaxy to infer its properties. One of the most compelling pieces of evidence comes from monitoring the orbits of stars extremely close to the black hole, such as the famous star S2, which completes a full orbit around the black hole in just over 16 years. The star travels at tremendous speeds, reaching thousands of kilometers per second at its closest approach, yet it follows a stable, predictable path dictated by the gravity of a single, enormously massive object. By calculating the gravitational influence required to keep S2 in orbit, scientists have confirmed that the mass of Sagittarius A star is indeed about 4 million times that of our Sun. And astonishingly, all this mass is confined within a region so compact that its radius is only about 17 light-hours, which is roughly 18 trillion meters, or about 114 times the distance from the Earth to the Sun. The comparison is mind-boggling. 4 million suns, almost unimaginably heavy, yet squeezed into a space that, on cosmic scales, is tiny. The very existence of such an object challenges our deepest intuitions about matter and space. In ordinary life, matter occupies space in proportion to its mass. A bigger object takes up more room. But at the heart of Sagittarius A star, this intuition fails. Gravity reigns supreme, compressing matter beyond any ordinary limit. The density becomes so extreme that the concept of volume loses its traditional meaning, and the singularity at the center represents a region where the equations of general relativity predict an infinite curvature of space-time. It is a place where the known laws of physics, laws that govern everything from falling apples to orbiting planets, reach their breaking point. The singularity is not just heavy, it is the ultimate concentration of mass in the universe, a place where space itself is warped, twisted, and pulled into unimaginable shapes. Yet despite its overwhelming mass and incomprehensible density, Sagittarius A star is not a cosmic vacuum cleaner indiscriminately swallowing everything in its vicinity. Its immense gravity dominates only the central region of the galaxy. Stars, gas clouds, and dust far enough away move in regular orbits, unaffected by its pull. In this sense, the black hole is like a cosmic anchor, holding the center of the Milky Way together while allowing the outer regions to revolve in a relatively stable dance. Observations using infrared telescopes, radio arrays, and X-ray satellites have allowed astronomers to map the motions of stars and gases with extraordinary precision. The data reveal a region of incredible activity and energy, where matter falling toward the black hole accelerates to near the speed of light, forming hot, luminous disks called accretion discs, which emit vast amounts of radiation. Occasionally, sudden flares erupt from the region, as clouds of gas are torn apart and swallowed, producing bursts of X-rays and other high-energy light. The mass of 4 million suns concentrated in a single point also raises profound questions about the origin and evolution of supermassive black holes. How does such an enormous object come to exist? Some scientists believe that black holes start small, formed from the collapse of the first generation of stars, and grow over billions of years by consuming gas, stars, and even other black holes. Others propose that they may form directly from massive clouds of gas collapsing under their own gravity in the earliest epochs of the universe. In either scenario, the final result is the same, a singularity containing millions, even billions, of times the mass of our Sun, a gravitational engine of unparalleled power at the heart of a galaxy. Understanding this process is crucial not only for astronomy, but for cosmology as a whole, because supermassive black holes are intimately connected to the formation and evolution of galaxies. Every large galaxy we know appears to harbour one at its centre, suggesting a deep and mysterious relationship between black holes and the galaxies that surround them. The implications of having 4 million suns in a single point extend beyond pure numbers. The immense gravity affects the passage of time itself. According to Einstein's theory of general relativity, time slows down in strong gravitational fields. Near the event horizon of Sagittarius A star, time for an observer would pass far more slowly than for someone at a safe distance. A star or spacecraft approaching the black hole would experience time dilation, witnessing the outside universe speeding by while its own clock ticks ever more slowly. Space is warped similarly, so that paths that appear straight to distant observers are dramatically curved near the singularity. Light bends, orbits precess, and the very structure of reality is distorted. For scientists and curious minds alike, this presents both a challenge and an opportunity. It allows tests of fundamental physics in extreme conditions, offering glimpses into phenomena that cannot be reproduced in any Earth-based laboratory. Studying Sagittarius A star is not merely an academic exercise. It has practical consequences for our understanding of the universe. By observing how matter behaves near such an extreme concentration of mass, astronomers gain insights into the behavior of plasma under intense gravity, the mechanics of relativistic jets, and the physics of accretion discs. These observations inform theories about the growth of black holes over cosmic time, the formation of galaxies, and even the distribution of dark matter. The black hole acts as a laboratory, albeit a natural one, where the laws of physics are pushed to their limits. It reveals a universe far stranger than the everyday world we experience, one in which matter can be crushed into a single point, light can be trapped forever, and time itself can be stretched and warped. Despite its incredible mass, the black hole is remarkably elusive. It cannot be seen directly because light cannot escape from it. Instead, astronomers detect its presence through indirect means: the orbits of nearby stars, the emission of X-rays and radio waves from infalling matter, and the gravitational effects on surrounding material. These observations require the most sophisticated instruments ever built, from radio interferometers stretching across continents to space-based telescopes capable of detecting faint infrared signals. The work is painstaking and requires decades of careful measurement, yet the results have been nothing short of revolutionary. They confirm that the heart of our galaxy hosts an object whose mass is inconceivable by ordinary human standards, concentrated into a point that defies the imagination. The notion of 4 million suns in a single point also invites reflection on our place in the cosmos. Earth and the solar system orbit a relatively quiet region of the Milky Way, safely far from the gravitational grip of Sagittarius A star. Yet, this massive object exerts an invisible influence on the galaxy as a whole, anchoring its spiral arms and shaping the motions of billions of stars. By studying supermassive black holes, we are not only uncovering the secrets of distant objects, we are also gaining perspective on the cosmic environment that has allowed life to emerge and flourish on our small planet. In many ways, the mass of 4 million suns in a single point is a symbol of the extremes of nature. It represents the ultimate triumph of gravity over matter, a place where energy, space, and time interact in ways that challenge human intuition. It is both terrifying and beautiful, a cosmic engine of incredible power and mystery. Each discovery about Sagittarius A star, each precise measurement of a star orbiting its center, each burst of X-rays captured by a telescope adds to our understanding of this extraordinary object. We are learning to measure the unmeasurable, to observe the invisible, and to imagine the unimaginable. The mass of 4 million suns in a single point is more than a number. It is a gateway to understanding the universe at its most extreme, a window into the forces that shape galaxies, stars, and planets, and a testament to the awe-inspiring power of nature. The more astronomers observe, the more fascinating the picture becomes. New technology allows us to see closer and closer to the event horizon, the boundary of no return. Observations in radio waves have revealed a complex structure of hot plasma, magnetic fields, and swirling matter near the black hole. In 2019, the first ever image of the shadow of a black hole, although of a different galaxy, was captured by the Event Horizon Telescope, proving that we can finally see the silhouette of these invisible giants. Such achievements bring us ever closer to visualizing the mass of 4 million suns compressed into a single point, and to understanding how such an object interacts with the rest of the galaxy. Even as we marvel at the enormity of Sagittarius A star, it is important to remember that our knowledge is still incomplete. The singularity itself, the exact nature of the point where all the mass resides, remains beyond the reach of current physics. Quantum effects, which dominate at extremely small scales, are likely crucial in understanding what happens inside a black hole. But a full theory combining quantum mechanics with general relativity has yet to be formulated. In this sense, the 4 million suns in a single point represent not only an extreme physical phenomenon, but also a profound scientific challenge. Throughout human history, we have always been drawn to the mysterious and the unknown. From the earliest cave paintings to modern science fiction, our imaginations have been captivated by the vast, uncharted spaces around us and the unseen forces that govern the cosmos. Among all these mysteries, perhaps none is more compelling, terrifying, and fascinating than the black hole. It is not merely a scientific phenomenon confined to textbooks and observatories. Black holes have become a cultural symbol of ultimate power, destruction, and inscrutable darkness. They are often described in literature, art, and conversation with words like the ultimate abyss, the cosmic monster, or the universe's heart of darkness. The metaphor that most captures our collective fear of these celestial objects is the idea of a demon. In human storytelling, demons are malevolent beings, powerful and incomprehensible, capable of swallowing souls, corrupting the living, and bending the natural order to their will. Black holes, in the minds of many, act as real cosmic demons, immense engines of gravity that consume everything in their path, even light itself. This metaphor is not a coincidence. It arises from both our visceral response to danger and the way black holes challenge our understanding of reality. When astronomers and physicists first described black holes in the early 20th century, their properties were already startling. These objects were predicted as a consequence of Albert Einstein's theory of general relativity, published in 1915, which described how mass and energy warp the very fabric of space and time. Initially, the concept was purely theoretical, regions of space where gravity becomes so intense that nothing, not even light, can escape. Such an idea was difficult for the human mind to grasp. Imagine a place in space where the usual rules of motion and matter no longer apply, where the familiar dance of planets, stars, and light is abruptly and utterly halted. It is a place where time itself slows down, seemingly to a halt at the very edge, called the event horizon. To a human being contemplating such an object from a safe distance, this is not only intellectually intimidating, it is psychologically unsettling. Here lies a structure that defies normal experience, something so extreme that it evokes the deepest instinctive fears we carry as creatures evolve to detect danger and preserve life. The demon metaphor is particularly powerful because it conveys not only the black hole's physical properties but also its existential threat. Demons in folklore are often associated with the unknown and the uncontrollable. They are beings that lie beyond human understanding, with motives and powers that cannot be predicted or countered. In a similar way, black holes challenge every notion of safety and stability that we take for granted in our daily lives. They are places where conventional physics breaks down, where matter is compressed to nearly infinite density, and where the familiar concepts of space and time dissolve. This is akin to the folkloric description of a demon's realm, incomprehensible, impenetrable, and dangerous. Even the names scientists use for black holes, the singularity, the event horizon, carry a subtle echo of the otherworldly, of boundaries we are warned not to cross. There is a linguistic resonance that reinforces our instinctive fear, merging the cold precision of science with the warm imaginative dread that stories of demons have carried for millennia. Beyond the linguistic and symbolic aspects, black holes are inherently dramatic. They are not static voids, but active and dynamic objects that interact violently with their surroundings. Gas, dust, and even entire stars that wander too close are torn apart and dragged into the black hole's maw, a process that releases staggering amounts of energy in the form of radiation. Quasars, for instance, which are powered by supermassive black holes at the centers of galaxies, can outshine entire galaxies of hundreds of billions of stars. Such events are far beyond the scale of everyday human experience, and this vastness itself can be terrifying. When we encounter forces so much larger, denser, and more powerful than ourselves, our brains instinctively categorize them as threats, even when we are physically safe. The demon metaphor bridges this cognitive gap. By imagining the black hole as a conscious, malevolent being, we create a narrative that helps us process and emotionally respond to something otherwise incomprehensible. There is also a deeply personal dimension to the fear that black holes evoke. Unlike comets, planets, or even asteroids, which exist on scales and timelines that allow for human observation and comprehension, black holes represent finality in the universe. Once matter passes the event horizon, it cannot return. This is ultimate loss, ultimate consumption, ultimate oblivion. For humans who are acutely aware of their own mortality, the idea of being irretrievably swallowed resonates with the existential fear of death itself. The demon metaphor is apt because demons often symbolize death, destruction, or the temptation to face forces beyond human control. Black holes are, in effect, impersonal cosmic demons. They do not plan or scheme, but the consequences of interacting with them are absolute and unyielding. This impersonal malevolence is eerily similar to the way demons operate in myth and folklore. They are indifferent to human suffering but capable of eradicating it entirely if the opportunity arises. Scientific observations over the past few decades have only intensified the sense of awe and fear surrounding black holes. In 1971, astronomers discovered the first strong candidate for a stellar mass black hole, Cygnus X1, in the constellation of Cygnus, approximately 6,000 light-years from Earth. This black hole, formed from the collapse of a massive star, demonstrated the ability to siphon material from its companion star, producing X-ray emissions that could be detected across vast distances. Later, in 2004, observations of stars orbiting the center of our Milky Way galaxy provided evidence for a supermassive black hole, now known as Sagittarius A, containing around 4 million times the mass of our Sun compressed into a region smaller than our solar system. The scale is incomprehensible, an object millions of times more massive than our star, yet invisible and defined only by its effect on nearby matter and light. To imagine such power is to confront a force far beyond human control, echoing the sense of helplessness that folklore often attributes to demons. The cinematic and literary portrayal of black holes has also cemented their association with fear. Science fiction frequently depicts them as portals to destruction, the ultimate cosmic trap from which no hero can escape. Films like Interstellar in 2014 dramatise the extreme gravitational effects near black holes, showing how time can stretch and twist, while novels and comic books often characterise them as ravenous voids that consume entire civilizations. These stories blend real science with human imagination, reinforcing the idea that black holes are not merely empty space but active agents of change and destruction. The demon metaphor is particularly effective here because it taps into deep-seated narrative instincts. Humans are naturally drawn to stories of confrontation with overwhelming power, and black holes offer a canvas for exploring the ultimate confrontation. Yet, despite the fear they inspire, black holes are also objects of fascination and curiosity. The very forces that make them terrifying also make them central to understanding the universe. By studying how matter behaves near a black hole, astronomers gain insight into gravity, relativity, and the fundamental laws that govern space and time. The extreme conditions near the event horizon act as natural laboratories, offering data that cannot be replicated on Earth. In this sense, the demon metaphor is double-edged. While black holes inspire fear, they also beckon, offering knowledge and insight to those brave enough to approach them intellectually. Humanity's fascination with black holes mirrors the way cultures have historically engaged with demons, with caution, reverence, and a mixture of fear and curiosity. There is also a cultural and psychological dimension to this fear. Black holes are universally present in human imagination because they embody both the unknown and the uncontrollable. They are distant yet omnipresent, invisible yet immensely influential. Black holes, in a scientific context, do something similar. They reflect the limits of human understanding and the fragility of matter and life in the face of cosmic forces. The metaphor is thus deeply resonant. By framing black holes as demons, humans are able to articulate complex scientific realities through a lens that is emotionally comprehensible, tapping into instincts honed over millennia of storytelling and survival. Moreover, the fear inspired by black holes is not static. It evolves as our understanding grows. In the 21st century, instruments like the Event Horizon Telescope, which in 2019 produced the first image of a black hole's shadow in the galaxy M87, have brought these cosmic demons closer to human perception. While the data demystifies some aspects of black holes, the underlying reality remains terrifying. The image itself, a dark, circular void surrounded by glowing, distorted light, resembles the classic depiction of a portal to an unknown, malevolent realm. The demon metaphor therefore persists, because even when we see black holes, we're confronted with their incomprehensibility and the sheer scale of their power. In addition, black holes play a unique role in the cosmic life cycle. Stars, galaxies, and even light itself interact with black holes in a dance of creation and destruction. Supermassive black holes anchor galaxies, regulating star formation and shaping galactic evolution. They act as both destroyers and sculptors, simultaneously consuming and creating in ways that echo mythic representations of demons who bring chaos but also change. This duality intensifies the metaphor. Like the demons of folklore, black holes are neither wholly evil nor benign. They are forces of nature, indifferent to morality, yet capable of outcomes that are awe-inspiring and terrifying in equal measure. Psychologically, humans are drawn to forces they cannot control because confronting them allows for imaginative exploration of fear in a safe way. The demon metaphor allows black holes to serve as objects of mental engagement, where we can explore the concepts of mortality, power, and the unknown without physical risk. By personifying black holes as demons, we give form to abstract dangers and gain a sense of narrative control over phenomena that are otherwise incomprehensible. In storytelling, education, and even casual conversation, the metaphor provides a bridge between raw scientific data and human experience, allowing us to emotionally process a universe that is otherwise indifferent to our presence. Even the terminology associated with black holes reinforces this perception. Terms like event horizon, singularity, spaghettification, and accretion disc are not just scientific jargon. They are linguistic signposts of danger and transformation. Event horizon implies a boundary beyond which nothing can return, a point of no escape. Singularity evokes an ultimate concentration of power and density, almost mystical in its finality. Spaghettification, a term coined to describe the stretching of objects falling into a black hole, carries a visceral, almost grotesque imagery. Together, these terms frame black holes as extreme alien entities that evoke the awe, terror, and fascination traditionally associated with demons. Since the earliest days of human storytelling, long before we could look through telescopes or measure the vast distances between stars, people have been fascinated by the night sky. The stars, the moon, the planets, and the occasional streaking comet were more than just points of light. They were signs, mysteries, and sometimes warnings. Among the most enduring and terrifying stories were those that imagined the cosmos as a place filled not only with beauty, but also with unimaginable danger. In countless ancient cultures across the world, humans spoke of cosmic monsters, devourers, and terrifying forces that lurked in the heavens, waiting to swallow worlds, stars, and even gods themselves. These myths are far more than fanciful stories. They reveal how people tried to make sense of the vast unknown, of forces far beyond their control, and of the unsettling idea that even the heavens could be hostile and unpredictable. Long before modern science gave us terms like black holes, supernovae, or gravitational collapse, human imagination filled in the gaps with stories of devouring entities in the sky. In Mesopotamia, one of the oldest known civilizations in human history, people spoke of Tiamat, a primordial goddess of saltwater, chaos, and creation. Tiamat was often depicted as a monstrous sea dragon or serpent. In the Babylonian creation epic, the Enuma Elish, Tiamat represents the untamed chaos of the universe. She's not merely a passive figure, but an active threat, seeking to engulf the emerging cosmos in her destructive, consuming waters. From the perspective of ancient Mesopotamians, the cosmos itself seemed to be teetering between order and chaos, creation and annihilation, with monsters like Tiamat symbolizing the terrifying possibility that everything could be undone. Similarly, in Norse mythology, the sky itself was a battleground, and monstrous beings roamed it with the potential to end the world. One of the most famous of these creatures is Jörmungandr, the world serpent, so vast that it encircles the earth, biting its own tail. Jörmungandr is a cosmic devourer in a very literal sense. Its eventual confrontation with the thunder god Thor during Ragnarok, the prophesied end of the world, symbolizes a cataclysmic consumption of everything familiar and safe. The Norse, living in a harsh and unpredictable northern environment, perhaps found this image of a monstrous serpent devouring the world a fitting reflection of the real dangers they faced in their lives, the sudden storms, harsh winters, and mysterious disappearance of people and animals. The night sky, with its unpredictable comets and eclipses, might well have been imagined as the eyes or breath of such a serpent, silently circling and watching. The Greeks too had their own visions of cosmic terror, often blending human-like intelligence with monstrous world-threatening forms. Typhon, for example, was a giant of terrifying strength and appearance, with hundreds of serpent heads and a voice that could shake the earth and sky. Typhon was said to challenge Zeus himself for dominion over the heavens, representing the chaotic forces that could disrupt the natural and divine order. In many ways, Typhon embodies an ancient recognition that the universe is not inherently orderly or safe. The forces behind the stars and the storms were unpredictable, mighty, and sometimes destructive. Even the stories of dragons in Greek mythology, which guarded treasures and secrets, suggest that the cosmos was thought to contain both wonders and terrors, hidden behind shimmering lights and distant, unreachable places. Moving eastward, the Hindu myths contain some of the most vividly terrifying cosmic monsters ever imagined. The universe in these stories is a cyclical battlefield, constantly created and destroyed by gods, demons, and cosmic forces. The serpent Vasuki, for instance, plays a central role in the churning of the cosmic ocean, an event that brings both creation and danger. In other myths, powerful demons or asuras are described as devourers, consuming not only people and animals but entire realms, challenging the gods themselves. The Hindu worldview often presents these cosmic threats as integral to the balance of the universe. Destruction is not merely evil, it is a necessary part of creation and renewal. Still, for ordinary humans hearing these stories, the message was clear. The universe is vast, incomprehensible, and filled with forces capable of swallowing everything in an instant. In the Americas, indigenous peoples also imagined devourers in the sky, though their forms were often uniquely tied to local environments and cosmologies. The Aztecs, for instance, spoke of cosmic deities who consumed and recreated worlds in cycles, often in violent and dramatic ways. The god Tezcatlipoca was both a creator and destroyer, whose gaze could unravel reality itself. Similarly, in the myths of the Inuit and other Arctic peoples, enormous sea creatures and sky beings were often imagined as swallowing the sun, moon, or even humans, explaining eclipses, storms, and other natural phenomena. These stories were not merely metaphors, they were attempts to make sense of the terrifying unpredictability of life in extreme environments, where survival often depended on respecting invisible forces and maintaining harmony with both nature and the cosmos. Across Africa, ancient myths also depict celestial monsters and devourers, often associated with serpents or crocodiles that could swallow the world or threaten the balance of creation. In some West African cosmologies, the sky itself is imagined as a living entity, and cosmic catastrophes are understood as conflicts between divine beings, some of whom take monstrous forms. Here again, the devourer is both a literal and symbolic presence, embodying the fears of death, chaos, and the unknown. It is fascinating to observe that these myths share striking similarities across continents and millennia. The devourer, whether dragon, serpent, giant, or demon, often represents a boundary between order and chaos, creation and destruction, life and death. These beings are not simply evil in the way modern stories might make villains evil. They are forces of nature, expressions of the universe's incomprehensible power. They embody the deep human intuition that the cosmos is vast and indifferent, capable of nurturing life one moment and destroying it the next. Ancient humans may not have understood gravitational forces, stellar collapse, or cosmic radiation, but through imagination, they captured the essence of these destructive yet awe-inspiring powers. Another striking aspect of these myths is their moral and philosophical dimension. Many of these devourers are not mindless. They act according to cosmic laws, divine edicts, or chaotic impulses that are beyond human understanding. They are, in a sense, the universe personified, given form and narrative so humans could relate to it. By imagining the cosmos as populated by monsters and devourers, ancient people were not merely telling scary stories, they were confronting the fundamental uncertainty of existence. Even more intriguingly, these myths often suggest a deep connection between destruction and rebirth. The devourer is not merely an agent of annihilation. In many stories, its actions make way for new creation. Tiamat's defeat by Marduk, Jormungandr's ultimate confrontation with Thor, and the cyclic battles between asuras and gods in Hindu myths all show that cosmic consumption is part of a larger rhythm. These myths reflect a profound awareness that the universe operates in cycles of birth, destruction, and renewal, concepts that resonate surprisingly well with modern scientific ideas about stellar life cycles, black holes, and cosmic evolution. Though ancient people lacked telescopes, mathematical equations, and the concept of gravity as we understand it, they intuited the same cosmic truth through metaphor, imagination, and myth. These devouring monsters are also deeply psychological symbols. They embody primal fears, fear of death, fear of the unknown, fear of forces that cannot be controlled. By projecting these fears into the sky and weaving them into stories, humans found a way to confront them indirectly. The monsters were terrifying, yes, but they could be understood, predicted, or appeased through ritual, prayer, and storytelling. Myths of cosmic devourers, therefore, were not only narratives about the universe, they were tools for psychological survival, helping humans cope with the vast, indifferent, and often dangerous world around them. Even today, these ancient myths continue to resonate. Modern astrophysics, with its black holes, neutron stars, supernova, and gamma-ray bursts, describes phenomena that are literally as terrifying and consuming as the monsters imagined by the ancients. The event horizon of a black hole, beyond which nothing can escape, is remarkably similar in concept to the cosmic devourers of myth, an invisible but absolute force capable of swallowing light, matter, and even time itself. In a way, the myths were not wrong. They were precursors to modern understanding, human attempts to describe and personify forces that were too vast and powerful to measure or fully comprehend. The persistence of these myths also highlights the universality of human experience. Across continents, from Mesopotamia to Scandinavia, from India to the Americas and Africa, people imagine similar cosmic monsters and devourers. Despite differences in geography, climate, and culture, the same basic themes recur: chaos versus order, destruction versus creation, fear versus awe. This suggests that the human mind, faced with the infinite night sky, naturally seeks patterns, explanations, and stories that make the terrifying unknown more comprehensible. In this sense, cosmic monsters are as much a part of the human imagination as they are of the universe itself. In some ways, these myths also convey a sense of humility. No matter how powerful a human might be, no matter how advanced a civilization becomes, the universe contains forces that are entirely beyond control. Ancient humans may not have understood gravity, nuclear fusion, or planetary orbits, but through stories of monsters and devourers, they grasped the essence of cosmic power. It is immense, indifferent, and often beyond human comprehension. The aesthetic of fear intertwined with wonder is another remarkable aspect of these myths. Cosmic devourers are terrifying, yes, but they also inspire awe. The night sky is not empty. It is alive with possibilities, dangers, and mysteries. Comets streak across the heavens like fiery serpents. Eclipses are the swallowing of the sun or moon, and meteor showers are showers of divine or monstrous wrath. Every celestial event is imbued with meaning, whether as warning, omen, or lesson. The myths teach humans to look at the universe not as a static backdrop, but as a dynamic, unpredictable, and sometimes hostile place, one that demands both respect and imagination. Even as societies evolved and scientific understanding grew, the motifs of cosmic devourers did not vanish. In literature, art, and cinema, these ancient fears continue to manifest. Modern science fiction and fantasy frequently depict monstrous entities consuming stars, planets, or entire civilizations. From the space-consuming monsters in contemporary novels and films to the abstract yet terrifying concepts of black holes and supernovae in scientific discourse, the same basic human fascination with cosmic consumption persists. Ancient myths and modern science thus meet in an unexpected harmony. Both reveal the grandeur, the terror, and the incomprehensibility of the universe. Another layer of these myths is their role in teaching moral, spiritual, and existential lessons. By personifying cosmic destruction in monstrous forms, ancient people were able to explore questions of destiny, choice, and morality. Who can challenge the devourer? How should humans behave when faced with forces they cannot control? What does it mean to survive in a world where annihilation is always a possibility? These myths do more than entertain. They provoke reflection on the human condition, mortality, and the nature of the universe itself. They are philosophical as much as they are narrative, blending cosmology, ethics, and imagination into cohesive, memorable stories. In the vast, silent stretches of the universe, where galaxies drift like islands in an endless cosmic ocean, black holes play a role far more intricate and surprising than the simple notion of being invisible, all-consuming monsters might suggest. These enigmatic entities, which range from relatively small stellar mass black holes to unimaginably enormous supermassive black holes at the hearts of galaxies, are not merely cosmic vacuums devouring everything in sight. Instead, they act as dynamic agents within the grand cycle of matter and energy, influencing the birth and evolution of stars in ways that are subtle, complex, and profound. The story of black holes and star formation is one of cosmic balance, violent explosions, and delicate threads of gas and dust dancing under the invisible sway of gravity. At first glance, black holes seem to be enemies of star formation. After all, their very definition is a region of space where gravity is so intense that not even light can escape. They are associated with the destruction of matter and the annihilation of anything that strays too close. And yet, as astronomers have discovered over the past century, the influence of black holes on the surrounding environment is not purely destructive. Instead, it can be paradoxically creative. Black holes exert what is known as feedback on their host galaxies, a term that describes how the energy they release can heat, compress, or otherwise reshape the surrounding gas. This feedback, while sometimes violent enough to blow gas out of a galaxy, can also compress clouds of gas in just the right way to ignite new generations of stars. Supermassive black holes, which sit at the center of nearly every large galaxy, are especially important in this process. These black holes contain millions, and in some cases billions of times the mass of our Sun, compacted into a space so small that if our Sun were replaced by such a black hole, it would fit inside a sphere no larger than the orbit of Mercury. The most famous of these is Sagittarius A star, located at the center of the Milky Way galaxy, which contains a mass of approximately 4 million suns in a single, invisible point. The immense gravitational pull of such black holes shapes the motion of stars, clouds of gas, and dust in their vicinity, creating dynamic environments where star formation can either flourish or be suppressed depending on local conditions. When matter spirals into a supermassive black hole, it rarely falls in smoothly. Instead, it forms what astronomers call an accretion disc, a rotating disk of gas and dust that heats up as it is squeezed by gravity, sometimes reaching temperatures of millions of degrees. This disk shines brilliantly in X-rays and other high-energy radiation, a beacon visible across millions of light-years. The energy released in this process can push on nearby gas, compressing it in certain regions while heating and dispersing it in others. In areas where gas is compressed, the increased density can trigger the collapse of gas clouds under their own gravity, the very first step in the birth of a star. In this way, the black hole becomes an indirect midwife of new stars, using its immense power not to destroy life but to set the stage for it. The influence of black holes on star formation is also deeply linked to their host galaxies' life cycles. In the early universe, just a few 100 million years after the Big Bang, galaxies were chaotic, gas-rich places. Supermassive black holes were already forming, growing rapidly as they devoured surrounding gas and merging with other black holes. The energy they released in the form of radiation and powerful jets, streams of particles traveling close to the speed of light, shaped the distribution of gas within these young galaxies. Observations of distant galaxies, whose light has travelled for more than 12 billion years to reach us, show that galaxies hosting rapidly growing black holes often have bursts of intense star formation. In these early times, the black holes and stars grew together, intertwined in a cosmic dance where the energy output of the black hole regulated the pace of star creation. Too much energy could blow gas out of the galaxy entirely, halting star formation, while moderate energy release could compress gas in clouds, igniting new stars. Even in modern galaxies, including our own Milky Way, this relationship persists. Regions near the center of our galaxy are dense with gas and dust, creating fertile grounds for star formation. Yet these regions are also influenced by Sagittarius A star. While this black hole is relatively quiet compared to the supermassive black holes in active galaxies, it occasionally emits bursts of energy that ripple through the surrounding medium. Such bursts, called flares, can heat local gas, pushing it into new configurations where gravitational collapse can occur. Over millions of years, this subtle push and pull helps regulate where and when new stars appear, maintaining a delicate balance between star formation and galactic stability. Stellar mass black holes, which form from the collapse of massive stars at the end of their lifetimes, also contribute to the cosmic ecosystem of star formation, though on smaller scales. When a massive star explodes as a supernova, it may leave behind a black hole, and the explosion itself injects enormous amounts of energy into the surrounding space. This energy compresses nearby gas clouds, triggering the collapse of regions that might eventually become new stars. Moreover, stellar mass black holes often exist in binary systems, drawing material from companion stars. The resulting outflows of energy and particles, though more localized than those of supermassive black holes, still influence the surrounding environment, sometimes creating pockets where star formation is enhanced. The process of star formation itself is profoundly influenced by the presence of black holes, because stars do not simply appear out of empty space. They are born from clouds of cold, dense gas. These clouds are susceptible to the slightest disturbances, and black holes provide a dramatic source of such disturbances. When a black hole releases energy, through jets, radiation, or accretion-related outflows, it can shock the surrounding gas, increasing pressure in certain regions and allowing gravity to take hold. In this way, black holes act as cosmic sculptors, shaping clouds of gas into filaments, clumps, and cores, which eventually collapse to form stars. Yet, the influence of black holes on star formation is not always positive. When energy output is extreme, as in active galactic nuclei, the radiation and jets can heat and disperse gas across vast regions, preventing it from cooling and condensing. This phenomenon, called quenching, can shut down star formation in entire galaxies. In some massive elliptical galaxies, astronomers observe that star formation has effectively ceased, and these galaxies are dominated by old red stars. The central black hole, through its feedback over billions of years, played a key role in creating this starless environment. Therefore, black holes are both creators and destroyers. Their energy can trigger starbirth in some places while halting it in others, depending on the intricate balance of forces and the availability of gas. Observational evidence for black holes' role in star formation comes from both nearby and distant galaxies. Telescopes like the Hubble Space Telescope, the Chandra X-ray Observatory, and the Atacama Large Millimeter-Submillimeter Array have revealed detailed images of galaxies where gas is being pushed and compressed by black hole activity. In some cases, astronomers see vast bubbles of hot gas, millions of light-years across, blown out by black holes, with denser filaments of cold gas at their edges where new stars are forming. In other galaxies, measurements of star formation rates correlate with the activity of central black holes, supporting the idea that black holes regulate the growth of their stellar neighborhoods. Theoretical models and computer simulations also illuminate the complex dance between black holes and star formation. Simulations that track the evolution of galaxies over billions of years show that galaxies without central black holes tend to form stars too quickly, consuming all their gas early and ending up with unrealistically high star densities. When black holes are included in the models, their feedback moderates the process, creating galaxies that resemble the ones we actually observe in the universe, galaxies with diverse star populations, realistic shapes, and stable structures. These simulations reveal that black holes, while small in size compared to the host galaxy, exert influence over scales hundreds of thousands of times larger than their own event horizons, shaping the destiny of millions of stars. The interplay between black holes and star formation also has profound implications for the chemical evolution of galaxies. Stars forge heavier elements in their cores, and when they die, they release these elements into space, enriching the interstellar medium. By influencing when and where stars form, black holes indirectly control the distribution of these elements, affecting future generations of stars and the potential for planetary systems like our own. In this sense, black holes are not just regulators of mass and energy, they are cosmic gardeners, influencing the chemical richness of galaxies and the potential for life-bearing worlds. Even the smallest details of star formation can be traced back to black holes. In starburst galaxies, where stars are being born at rates hundreds of times faster than in the Milky Way, the intense activity of central supermassive black holes is often evident. Jets and winds from these black holes stir the gas, creating turbulence that fragments clouds into clumps that collapse into stars. Conversely, in more quiescent galaxies, black holes can maintain a steady environment where star formation proceeds more slowly, preserving gas for longer periods. This duality, both stimulating and suppressing starbirth, is a hallmark of black hole influence throughout cosmic history. In the vast expanse of the universe, our home galaxy, the Milky Way, holds many secrets. One of the most intriguing discoveries in recent times is the phenomenon known as the Fermi Bubbles. These are two enormous structures of gas and cosmic rays that extend high above and below the centre of our galaxy. Their discovery has opened up new avenues of research and has left scientists pondering their origins and implications. The Fermi Bubbles were first detected in the year 2010 by the Fermi Gamma Ray Space Telescope, a project of NASA. This telescope is designed to observe gamma rays, which are the highest energy form of light. The discovery was made when astronomers noticed two large symmetrical regions emitting high-energy gamma rays. These regions, or bubbles, are centered on the galactic core and extend about 25,000 light-years above and below the plane of the Milky Way. To put this into perspective, the entire Milky Way galaxy spans about 100,000 light-years in diameter, making these bubbles a significant feature in our galactic neighborhood. What makes the Fermi Bubbles particularly fascinating is their composition and structure. They are filled with cosmic rays, high-energy particles such as protons and electrons, and are surrounded by hot, ionized gas. The gamma rays detected by the Fermi telescope are produced when these cosmic rays interact with lower-energy photons, a process known as inverse Compton scattering. This interaction results in the emission of gamma rays, which are then detected by the telescope. The size and symmetry of the Fermi Bubbles suggest that they are not random occurrences, but are likely the result of a significant event or series of events. However, the exact cause of their formation remains a subject of intense study and debate among astronomers and astrophysicists. One leading hypothesis is that the Fermi Bubbles were created by an energetic outburst from the supermassive black hole located at the center of the Milky Way, known as Sagittarius A. This black hole has a mass equivalent to about 4 million times that of our Sun. The theory posits that several million years ago, Sagittarius A experienced a period of intense activity, possibly consuming a large amount of gas or stars. This activity could have released a tremendous amount of energy, propelling matter outward and forming the bubbles we observe today. Supporting this hypothesis is the discovery of similar structures in other galaxies. Observations have shown that many galaxies with active supermassive black holes exhibit features resembling the Fermi Bubbles. This suggests that such outbursts are not unique to our galaxy, but are a common phenomenon in the universe. Another theory proposes that the Fermi Bubbles resulted from a massive star formation event, or starburst, at the galactic center. In this scenario, the rapid formation of a large number of massive stars would have led to numerous supernova explosions. The energy released by these explosions could have driven gas and dust outward, creating the bubbles. This theory is supported by observations of other galaxies where similar starburst activities have led to the formation of large-scale outflows. Despite these theories, the exact mechanism behind the creation of the Fermi Bubbles is still not fully understood. The complexity of the interactions involved and the scale of the structures make it challenging to pinpoint a definitive cause. Ongoing observations and simulations continue to provide new insights, but the mystery persists. The study of the Fermi Bubbles is not just about understanding a peculiar feature of our galaxy. It also offers valuable information about the processes occurring at the centers of galaxies in general. The activity of supermassive black holes, the dynamics of cosmic rays, and the behavior of hot gas are all interconnected and play crucial roles in the evolution of galaxies. In addition to the Fermi Bubbles, another significant discovery has been made in the study of our galaxy's center. In the year 2025, astronomers using the Green Bank telescope observed cold hydrogen gas clouds within the Fermi Bubbles. These clouds, described as ice cubes, are located in regions where such cold gas was not expected to exist due to the intense heat of the surrounding plasma. The presence of these cold clouds challenges previous assumptions and suggests that the processes occurring in the galactic center are more complex than previously thought. These findings have important implications for our understanding of galactic evolution. The survival of cold gas in such extreme conditions indicates that the mechanisms governing the behavior of matter in the galactic center are not fully understood. It also raises questions about the role of such gas in the formation of stars and other structures within the galaxy. The discovery of the Fermi Bubbles and the subsequent observations have sparked a renewed interest in the study of our galaxy's center. They have highlighted the need for more detailed observations and more sophisticated models to explain the phenomena occurring there. As technology advances and our observational capabilities improve, it is likely that we will uncover more about these enigmatic structures and their role in the broader context of galactic evolution. Einstein's theories, particularly his general theory of relativity, have reshaped the way humans perceive the universe, and their influence becomes even more profound when applied to the mysterious and extreme environment at the centre of our Milky Way galaxy. At the heart of this cosmic swirl lies Sagittarius A, a supermassive black hole with a mass equivalent to approximately 4 million suns, compacted into a space so small that imagining it stretches the limits of human understanding. It is here, in the very centre of our galaxy, that Einstein's ideas about gravity, space and time come alive, revealing themselves in phenomena that seem almost like the stuff of science fiction, yet are very real and observable through modern astronomical instruments. Einstein's general theory of relativity, proposed in the year 1915, revolutionized the understanding of gravity. Unlike Newtonian physics, which treated gravity as a force acting at a distance, Einstein described gravity as the bending and warping of space and time itself, caused by the presence of mass and energy. Massive objects like stars, planets, and especially black holes distort the fabric of the cosmos around them, creating a curvature that directs the paths of other objects and light. Near a black hole like Sagittarius A, this curvature becomes extreme, producing effects so intense that they challenge intuition. Light itself, normally thought to travel in straight lines, bends around the black hole in ways predicted precisely by Einstein's equations, creating gravitational lensing and other dramatic visual effects observable from Earth. In the dense star cluster surrounding Sagittarius A, stars orbit at tremendous speeds, some of them moving at a few percent of the speed of light, tracing paths that can only be accurately described using general relativity. A particularly famous star, known as S2 or S02, has an orbit that lasts approximately 16 years, approaching as close as 17 light hours to the black hole at its nearest point, a distance unimaginably small when compared to the vastness of the galaxy. Observing S2 and other nearby stars provides astronomers with a natural laboratory for testing Einstein's predictions. The precise motion of these stars, including the precession of their orbits, mirrors the relativistic corrections that Newtonian physics cannot account for. These observations have confirmed time and again that Einstein's theory, developed more than a century ago, still stands as the most accurate description of how gravity operates in the most extreme conditions known to science. Time itself behaves strangely in the vicinity of Sagittarius A. According to general relativity, the closer an object is to a massive gravitational source, the slower time moves relative to an observer farther away. This phenomenon, known as gravitational time dilation, means that clocks near the black hole tick more slowly than those on Earth. While the differences are imperceptible for everyday experiences on our planet, near a supermassive black hole, these effects are magnified enormously. Astronomers must account for this distortion when calculating orbits and predicting the behaviour of stars and gas near the galactic core. In a sense, S2 and other stars in close orbit around Sagittarius A experience a different flow of time than we do, living a few seconds behind or ahead compared to distant observers over years of observation. Einstein's theories also illuminate the violent events that occasionally erupt near the galactic core. Sagittarius A, despite being relatively quiet today, is far from inactive. X-ray flares and radio outbursts periodically signal that matter from the surrounding environment is falling into the black hole, releasing enormous amounts of energy as it is heated to millions of degrees. The motion of this matter, the way it spirals inward and accelerates to nearly the speed of a light, and the way it radiates energy are all governed by the intricate mathematics of general relativity. Without Einstein's framework, understanding the dynamics of accretion discs and predicting the behaviour of this matter as it approaches the event horizon would be nearly impossible. Observations of these flares, using space-based telescopes sensitive to X-rays and infrared light, have repeatedly validated the theory's predictions. The extreme gravitational field near Sagittarius A also causes the phenomenon of gravitational redshift, where light escaping from the black hole's vicinity loses energy and shifts toward longer wavelengths. This effect, first predicted by Einstein, has been observed in the spectra of stars and gas near the galactic centre. Measuring this redshift allows astronomers to estimate the gravitational strength and confirm the mass of the black hole with remarkable precision. In the year 2012, a team of astronomers reported observing such relativistic effects in the orbit of star S2 during its closest approach, providing one of the most direct confirmations of general relativity in the strong gravity regime. These results offered not only a validation of Einstein's theory, but also a deeper understanding of the structure and behavior of our galaxy's central engine. Even the seemingly empty space around Sagittarius A is shaped by Einstein's ideas. The bending of light caused by the black hole distorts the appearance of background stars, creating arcs and smears that act as a natural lens, magnifying distant objects. This gravitational lensing effect, which has been observed in countless galaxies across the universe, becomes particularly intense near supermassive black holes. Light, although massless, follows the curved space-time, revealing the profound truth that space itself is not merely an empty stage upon which celestial objects move, but a dynamic and malleable fabric that interacts with matter and energy. The galactic core, dense and turbulent, provides an extraordinary setting in which these principles manifest visibly, allowing astronomers to test and refine their understanding with unprecedented clarity. Einstein's theory also predicts the existence of phenomena that are nearly impossible to observe directly, but whose influence is undeniable. Among these are gravitational waves, ripples in space-time produced by the acceleration of massive objects. While the merger of stellar mass black holes produces waves detectable across vast distances, the supermassive black hole at the center of the Milky Way could generate low-frequency waves if it were to interact with another massive object. These waves, traveling at the speed of light, stretch and compress space as they pass, confirming the dynamic and flexible nature of the universe described by general relativity. The detection of gravitational waves in the 21st century, a century after Einstein first predicted them, has opened an entirely new window onto the cosmos, allowing scientists to hear the universe in a way that complements the visual observations of light, X-rays, and radio waves. Relativity also provides crucial insights into the ultimate fate of objects that venture too close to Sagittarius A. The event horizon, the boundary beyond which nothing can escape the black hole's grip, marks the limit of classical physics. Within this region, gravitational forces become so intense that all known laws of physics are pushed to their limits. Matter that crosses this threshold is compressed to extraordinary densities, and space and time themselves are so warped that the future of that matter is effectively sealed. Einstein's equations describe the approach to this boundary with incredible precision, revealing the extreme tidal forces and spaghettification effects that objects would endure. Although no human-made probe has ever approached even remotely close to a supermassive black hole, simulations based on relativity provide a vivid picture of the dramatic transformations that occur in this region. Beyond the immediate surroundings of Sagittarius A, Einstein's theories help explain the behavior of stars and gas on a galactic scale. The rotation of the Milky Way, the distribution of mass in the galactic disk and bulge, and the dynamics of globular clusters near the core all reveal subtle but measurable relativistic effects. Even though these effects are smaller than those near the black hole, they accumulate over millions of years, influencing the evolution of the galaxy itself. General relativity, therefore, is not merely a local curiosity confined to extreme objects, but a fundamental principle shaping the structure and motion of entire galaxies. The ongoing observation of the galactic center has also provided opportunities to explore the interplay between Einstein's theory and quantum mechanics, the other great pillar of modern physics. Near the event horizon, where gravitational fields are incredibly strong and matter is compressed to extreme densities, the predictions of relativity brush up against the probabilistic and discrete nature of quantum physics. This interface is one of the most profound mysteries in contemporary science, inspiring theories such as quantum gravity, string theory, and the holographic principle. Studying Sagittarius A allows scientists to probe these boundaries indirectly, providing clues about how the universe operates at its most fundamental level, where space, time, matter, and energy converge in ways that challenge even the most brilliant human minds. Einstein's influence extends even to the practical methods of observation and data interpretation. Techniques such as very long baseline interferometry, which link radio telescopes around the globe to achieve incredible resolution, are designed with relativistic effects in mind. The bending of light, the delay of signals due to gravity, and the need to account for time dilation are all critical in producing accurate images of the galactic center. The Event Horizon Telescope's famous image of a black hole in the galaxy M87 in the year 2019, while not Sagittarius A, relied on these principles and provided a preview of what scientists hope to achieve in imaging the Milky Way's central black hole. When such an image is obtained, it will not only confirm the predictions of general relativity yet again, but will also offer humanity its first direct visual glimpse of the very fabric of space and time in one of its most extreme manifestations. Throughout all these explorations, Einstein's theories have remained an indispensable guide. From predicting the motion of stars and the bending of light to explaining high-energy flares and the extreme warping of spacetime near the event horizon, general relativity provides a framework within which the galactic center can be understood. Each new observation, whether of a distant star's orbit, a flash of X-rays, or a subtle gravitational lensing effect, adds to the growing body of evidence that Einstein's vision of the universe, conceived more than 100 years ago, continues to illuminate the cosmos in ways that are both profound and awe-inspiring. The galactic core, once an abstract and inaccessible region, now serves as a tangible testament to the power of human intellect and the enduring truth of scientific discovery, where the interplay of mass, energy, space, and time unfolds according to the principles that Einstein first set down with elegance and precision in the early years of the 20th century. In this cosmic theatre, where stars dance under the influence of an unseen maestro and light bends around invisible boundaries, Einstein's theories come alive. They are not just abstract equations written on paper, but living rules of a universe that challenges perception, ignites curiosity, and inspires wonder. The central black hole of our galaxy, while hidden from direct view, speaks volumes through its influence on surrounding matter, a silent echo of the curvature of space-time, a proof that gravity is not merely a force, but a manifestation of the very structure of reality. Imagine for a moment looking toward the center of the galaxy, a distance of about 26,000 light-years from Earth, which is roughly 243 quintillion kilometers, a number so large it's almost impossible to truly grasp. There, in that seemingly empty, dark region, lies an object so powerful that its gravity bends the very fabric of space and time around it, an object whose existence allows scientists to explore the most extreme predictions of Albert Einstein's theory of general relativity. General relativity, formulated by Einstein over 100 years ago in 1914, describes gravity not as a force, like Newton imagined, but as the warping of space and time by mass and energy. Massive objects such as stars, planets, or black holes bend the surrounding space-time like a heavy ball pressed into a stretched rubber sheet. Light and matter moving nearby follow the curves in this space-time, producing what we perceive as gravitational attraction. While Einstein's theory has been tested repeatedly in our solar system and on Earth, Sagittarius A offers an unparalleled laboratory to push these tests to the absolute limit, because nothing else in the galaxy approaches the combination of mass, density, and proximity to other stars that Sgr A does. Sagittarius A contains a mass equivalent to about 4 million suns packed into a volume no larger than our solar system. To put that into perspective, imagine squeezing all the stars you see on a clear night in the sky into a region smaller than the orbit of Pluto. The gravity near such an object is so intense that it dramatically warps space-time, causing light to bend sharply, time to slow noticeably, and matter to accelerate to enormous speeds as it falls toward the event horizon, the boundary beyond which nothing, not even light, can escape. Observing these effects from Earth allows astronomers to see Einstein's predictions in action under conditions that are far more extreme than anything found in the solar system. One of the most famous tests of relativity near Sagittarius A comes from tracking the motion of individual stars that orbit the black hole. Among these stars, one has captured particular attention, a star known as S2, also called S02. SS2 completes an orbit around the black hole in roughly 16 years, travelling along a highly elongated or elliptical path. Its closest approach brings it within about 17 light-hours from the black hole, which is approximately 18 trillion meters. At that proximity, S2 reaches astonishing speeds of up to 25 million kilometers per hour, about 3% of the speed of light, racing through the warped space-time near the heart of the galaxy. By observing S2 over decades, astronomers have been able to measure tiny deviations in its orbit, precisely those deviations predicted by Einstein's general relativity. For instance, as S2 swings around Sagittarius A, its orbit does not remain fixed like a planet circling the Sun. Instead, the closest point of approach, called the pericenter, shifts gradually with each orbit in a phenomenon known as orbital precession. This is exactly what general relativity predicts. The gravitational field of such a massive compact object is so strong that it twists the orbit of any nearby star over time. Detecting this shift requires incredibly precise measurements, down to fractions of a milliarc second, which is like trying to measure the width of a human hair from more than 6,000 kilometers away. In 2017, astronomers announced that they had finally observed this precession in S2's orbit, providing one of the clearest confirmations yet that Einstein's equations describe the motion of objects in the extreme gravitational field of a supermassive black hole. But S2 is not the only star revealing the secrets of Sagittarius A. The galactic center is surrounded by a cluster of stars known as the star cluster, many of which also follow tight orbits around the black hole. Each of these stars acts like a test particle moving through a natural laboratory of extreme gravity. By tracking the velocities and positions of dozens of these stars over time, astronomers can map the gravitational field of Sagittarius A with remarkable accuracy, testing predictions of general relativity, measuring the mass of the black hole, and even constraining the distribution of unseen matter, such as dark matter or smaller black holes, near the galactic center. In addition to stellar orbits, the behavior of light near Sagittarius A provides another avenue to explore relativity. Light passing close to the black hole does not travel in a straight line. Instead, it bends in response to the curvature of space-time. This gravitational lensing effect can cause stars and other background objects to appear in slightly shifted positions, distorted, or even multiply imaged. Observing such subtle distortions allows astronomers not only to test Einstein's theory, but also to probe the immediate environment around the black hole, including the presence of hot gas, dust, and even the influence of magnetic fields, all of which interact in complex ways with the curved space-time. Sagittarius A also provides a rare opportunity to study the behavior of time itself. One of the most extraordinary predictions of general relativity is time dilation in strong gravitational fields. Clocks closer to a massive object tick more slowly compared to clocks farther away. While this effect is tiny on Earth or in the solar system, near a supermassive black hole like Sagittarius A, it becomes significant. Observations of stars like S2 during their closest approaches allow astronomers to detect this gravitational time dilation by comparing the apparent speed of motion and the shifting frequencies of light emitted by the star. In 2018, researchers reported measurements that directly detected this effect, confirming that time indeed slows down in the presence of extremely strong gravity, just as Einstein had predicted more than a century earlier. The study of flares from Sagittarius A adds yet another layer of intrigue. Occasionally, the black hole emits bursts of X-rays and infrared light, likely caused by hot gas and dust spiraling into its depths. These flares provide additional tests of relativity, because the motion of the emitting material is governed by the warped space-time close to the event horizon. By carefully tracking the timing, intensity, and spectral properties of these flares, astronomers can infer the geometry of the black hole's surroundings, the speed of infalling matter, and the effects of extreme gravity on radiation. These observations push the limits of both observational technology and theoretical models, revealing details that were unimaginable even a few decades ago. Technological advancements have been critical to making these discoveries possible. Telescopes equipped with adaptive optics, such as the Very Large Telescope in Chile, can correct for the blurring effects of Earth's atmosphere, allowing astronomers to resolve individual stars near the black hole with unprecedented clarity. Similarly, instruments like the Gravity Interferometer combine the light from multiple telescopes to achieve the resolution of a telescope several hundred meters across, enabling precise measurements of stellar positions and motions near Sagittarius A. These tools have transformed the galactic center from an inaccessible region into a laboratory where the most extreme predictions of physics can be tested directly. The detection of gravitational redshift in the light from stars orbiting Sagittarius A represents another triumph. As light climbs out of the deep gravitational well of the black hole, it loses energy, shifting toward longer wavelengths, or the red end of the spectrum. This effect, predicted by general relativity, was first confirmed in Earth-based experiments, but observing it near a supermassive black hole is a far more extreme and striking demonstration. During S2's closest approach in 2018, astronomers measured precisely this shift, providing yet another direct confirmation of Einstein's theory in one of the most extreme environments in the universe. Sagittarius A also serves as a bridge between theory and observation in the quest to understand black holes more generally. While general relativity predicts the existence of event horizons and singularities, regions of infinite density where classical physics breaks down, the actual behavior of matter and radiation near such boundaries remains a topic of intense research. By observing stars, gas, and light near Sagittarius A, astronomers gain insights into phenomena such as accretion discs, relativistic jets, and even the possible effects of quantum gravity at the edge of a black hole. Each measurement, each flare, and each orbit adds to a growing picture of how matter behaves under conditions that cannot be replicated in any laboratory on Earth. Furthermore, the motion of stars and gas near Sagittarius A can potentially reveal deviations from general relativity or hints of new physics. While Einstein's theory has passed every test so far, scientists remain alert to anomalies such as unexpected orbital shifts, unusual precession patterns, or discrepancies in gravitational lensing, which could suggest modifications to our understanding of gravity. The galactic center thus functions as both a confirmation and a challenge, pushing theoretical physics to explore the boundaries of knowledge, from classical general relativity to quantum corrections that may emerge in the future. The extreme environment around Sagittarius A is not static. Stars and gas clouds interact dynamically, sometimes being torn apart or flung outward by the black hole's gravitational pull. A famous example occurred in 2013 when a gas cloud known as G2 approached Sagittarius A on a highly elliptical orbit. Astronomers watched with intense anticipation to see whether the cloud would be disrupted or captured by the black hole. While the outcome was more subtle than dramatic, the event offered a unique opportunity to observe how matter behaves under the influence of a supermassive black hole, providing further tests of relativistic predictions in real time. Even light that barely grazes the black hole provides insights. Photons passing close to the event horizon follow paths that are highly curved, leading to phenomena such as gravitational lensing and the formation of photon rings, circular patterns of light predicted by general relativity. Recent advances, including the imaging of the shadow of the black hole by the Event Horizon Telescope in 2019, have revealed the silhouette of Sagittarius A against the glowing background of infalling hot gas. This shadow, shaped by the extreme warping of space-time, provides a striking visual confirmation of Einstein's equations and a direct glimpse of a black hole's presence, long predicted but only recently seen. Sagittarius A also allows the testing of relativity in combination with other physical effects. For example, the black hole's spin, or angular momentum, influences the orbits of nearby stars and the paths of light. Frame dragging, an effect predicted by general relativity in which a rotating massive object twists the surrounding spacetime, can subtly alter the motion of matter and light near the black hole. Detecting these tiny distortions requires extraordinary precision, but they offer a window into the most intricate predictions of relativistic physics, revealing how rotation and mass together shape the cosmos. The study of Sagittarius A has implications beyond our galaxy. Supermassive black holes are thought to reside at the centers of most galaxies, influencing the formation, evolution, and dynamics of their host galaxies. By understanding how stars, gas, and light behave near our own central black hole, astronomers can infer the behavior of black holes millions or even billions of times more massive in distant galaxies. In this sense, Sagittarius A is both unique and representative, serving as a nearby laboratory for exploring universal principles of gravity, matter, and energy. Despite its extreme environment, Sagittarius A is surprisingly quiet compared to other supermassive black holes. Unlike the luminous quasars that blaze across the universe, Sgr A emits only modest radiation, primarily in the radio, infrared, and X-ray bands. This relative calm allows astronomers to study the motions of individual stars with minimal interference from the black hole's own energetic outbursts, providing a rare opportunity to isolate the pure effects of extreme gravity without overwhelming background noise. Even the occasional flares become valuable probes, rather than sources of confusion, enabling tests of relativistic predictions under controlled observable conditions. The journey of exploring Sagittarius A is ongoing, with each year bringing new observations, improved techniques, and refined theoretical models. The continued monitoring of stars like S2, along with the discovery of new stars and gas clouds, expands the range of tests available, probing ever closer to the event horizon. Adaptive optics, interferometry, and other cutting-edge technologies will push the limits of resolution and sensitivity, allowing astronomers to detect even finer effects predicted by general relativity, including subtle precession patterns, gravitational redshifts, and frame-dragging influences. Every new measurement adds a piece to the puzzle, deepening our understanding of gravity in its most extreme manifestation. Sagittarius A does more than test the limits of relativity. It also inspires profound philosophical reflection. To contemplate an object so massive, dense, and mysterious challenges our intuition about space, time, and matter. The very notion that time itself can slow, that space can bend, and that matter can vanish beyond an invisible boundary stretches the human imagination. Observing stars like S2, racing through warped space-time, or witnessing the shadow of the black hole against the glowing background of infalling gas, evokes a sense of wonder and humility. The supermassive black hole at the heart of the Milky Way is thus a cosmic laboratory unlike any other. It allows astronomers to test Einstein's general relativity under conditions of extreme mass, density, and velocity, providing insights that cannot be gained elsewhere in the galaxy or solar system. By studying the orbits of stars, the behavior of light, and the dynamics of gas and flares near Sagittarius A, scientists continue to confirm the predictions of relativity, explore the boundaries of known physics, and push the limits of observational astronomy. Each observation reinforces the extraordinary vision of Einstein, whose equations, written more than 100 years ago, continue to describe the behavior of objects in the most extreme corners of our galaxy. Yet, even with all we have learned, Sagittarius A keeps many secrets. The details of its spin, the precise nature of its immediate surroundings, the potential presence of additional compact objects nearby, and the ultimate fate of infalling matter remain active areas of research. As astronomers continue to monitor the galactic center, combining data from optical, infrared, radio, and X-ray telescopes, the interplay between observation and theory will deepen our understanding of black holes, gravity, and the fundamental structure of the universe itself. In this way, Sagittarius A is not only a test of Einstein's theory, but also a beacon guiding humanity's exploration of the cosmos. In the vast and mysterious tapestry of our universe, there exist objects so powerful, so enigmatic, and so terrifying that they seem to defy the very laws of nature themselves. Among these cosmic wonders, black holes stand as the ultimate devourers, celestial beasts whose hunger is limitless, whose appetites shape the very galaxies around them, and whose influence stretches across the cosmos in ways that continue to challenge our understanding. Black holes, often imagined as simple points of darkness, are far more dynamic and dramatic than most people realize. They are not just passive voids that swallow everything that comes near. They are active participants in a cosmic dance of creation and destruction, governing the lives of stars, gas, and dust in a spectacle that can only be described as a galactic banquet, a chaotic feast of extraordinary proportions. When a black hole feeds, it does not simply open its mouth and consume silently. The process is violent, energetic, and awe-inspiring. The simplest way to imagine it is to picture a vast whirlpool in the fabric of space, pulling everything, stars, clouds of gas, stray dust, toward its center. But unlike a whirlpool in water, this cosmic maelstrom twists, stretches, and accelerates matter to incredible speeds, heating it to temperatures that can reach millions, sometimes tens of millions of degrees. At these unimaginable temperatures, matter glows with brilliant light across the electromagnetic spectrum. To observers with powerful telescopes, the feeding of a black hole is a spectacular light show, shining in X-rays, gamma rays, and radio waves, far outshining the combined light of millions or even billions of stars in its host galaxy. One of the most fascinating aspects of black hole feeding is the formation of what astronomers call an accretion disk. This is a spinning, flattened structure of gas, dust, and debris that swirls in a tightly wound spiral as it is drawn toward the black hole. The matter in the accretion disk does not fall in immediately. Instead, it orbits the black hole thousands, even millions of times, heating up more and more with every revolution. Friction, magnetic forces, and gravitational energy work together to create a furnace hotter than anything humans can replicate on Earth. This spinning disk can extend across distances larger than our entire solar system, a vast cosmic carousel where material races around the black hole at velocities approaching the speed of light. The closer the material gets to the black hole, the faster it spins, until finally, some of it plunges past the point of no return, the event horizon, vanishing forever from our universe. Yet, the story of black hole feeding is not limited to the quiet, invisible disappearance of matter. The feeding process is often accompanied by violent eruptions, cosmic fireworks that project streams of energy and matter into intergalactic space. These are the famous relativistic jets, narrow beams of particles travelling at nearly the speed of light, powered by the intense gravitational and magnetic forces near the black hole's event horizon. These jets can extend for hundreds of thousands, even millions of light years, piercing the cosmic darkness like lances of pure energy. They can sculpt entire galaxies, triggering star formation in some regions while halting it in others, a paradoxical influence that underscores the chaotic and unpredictable nature of black holes. The energy released by these jets can rival or even exceed the combined luminosity of every star in the host galaxy, demonstrating the staggering scale of a black hole's appetite and its ability to reshape the cosmos. The feeding habits of black holes are not uniform or predictable. Some black holes gorge themselves in sudden dramatic bursts, consuming enormous clouds of gas in mere years or decades. Others feed slowly, drawing in matter at a leisurely pace over millions of years, their effects subtle yet profound. Astronomers have observed black holes devouring entire stars in a process known as a tidal disruption event. In these rare but spectacular occurrences, a star strays too close to the black hole and is torn apart by gravitational forces, its material stretched into a thin stream, some of which spirals into the black hole while the rest is ejected outward in a brilliant flare of light. These events are not just destructive, they illuminate the environment around black holes, providing invaluable insights into the behavior of matter under extreme conditions, the dynamics of gravity, and the interplay of light and energy near the most extreme objects in the universe. At the heart of nearly every galaxy lies a supermassive black hole, millions to billions of times the mass of our Sun. These behemoths act as the central engines of galactic evolution, regulating the growth of stars and the distribution of matter within their host galaxies. When a supermassive black hole feeds, it can trigger waves of turbulence throughout the galaxy, heating gas, stirring star-forming clouds, and sometimes ejecting material entirely into intergalactic space. This process, known as feedback, is a central component of the life cycle of galaxies, linking the microcosmic realm of black holes to the grand architecture of the cosmos itself. The chaos that erupts from feeding events can appear random, yet it follows a deep cosmic logic, a balancing act between creation and destruction that ensures galaxies neither collapse under their own gravity nor disperse into empty space. The feeding of black holes also plays a crucial role in cosmic chemistry. The violent environments around these devouring monsters are laboratories where atoms are stripped of their electrons, elements are forged in intense nuclear reactions, and high-energy particles are accelerated to nearly light speed. The material expelled from black holes enriches the surrounding interstellar medium with heavy elements, seeding the next generations of stars and planets. In this way, black holes are not merely destroyers, they are paradoxically creators, distributing the ingredients necessary for life across the galaxy, linking the end of one star to the birth of countless others in an endless cycle of cosmic renewal. Observing black holes feeding is not a simple task. Despite their tremendous influence, black holes themselves are invisible, detectable only through their interactions with nearby matter and the gravitational waves they produce. Astronomers rely on the brilliant emissions from accretion discs, the sweeping jets of energy, and the occasional flare from a disrupted star to study these objects. Observatories such as the Chandra X-ray Observatory, the Hubble Space Telescope, and the Event Horizon Telescope have revealed glimpses of these feeding events with unprecedented clarity. In 2019, the Event Horizon Telescope produced the first ever image of the shadow of a supermassive black hole in the galaxy Messier 1619, providing direct visual evidence of the violent environment at the edge of an event horizon. These observations are transforming our understanding of black holes from theoretical curiosities into tangible, observable forces that shape the universe on the grandest scales. Even smaller black holes, those born from the deaths of massive stars, exhibit equally dramatic feeding behavior. When a star in a binary system ventures too close to its black hole companion, it can be stripped of its outer layers, forming an accretion disk that shines brightly in X-rays. These stellar mass black holes act as cosmic cannibals, consuming matter with a hunger that can rival their supermassive cousins, albeit on a smaller scale. Their feeding provides laboratories for studying extreme physics, from relativistic effects to magnetic turbulence, giving astronomers insights into phenomena that cannot be replicated on Earth. The chaotic nature of black hole feeding is not just a cosmic spectacle, it has profound implications for the evolution of galaxies and the universe itself. By regulating star formation, distributing elements, and influencing the motion of gas and dust, black holes act as both destroyers and creators, catalysts for change in the cosmic ecosystem. Their feast can ignite new generations of stars, trigger the formation of massive star clusters, and sculpt the structure of entire galaxies. Yet they can also halt star formation, expel gas, and leave galaxies quiescent. As we continue to study black holes, the mysteries deepen. What triggers the most extreme feeding events? How do magnetic fields and relativistic effects shape the accretion process? What role do black holes play in the formation of the earliest galaxies, nearly 14 billion years ago? Each new observation adds a piece to the puzzle, revealing a universe that is dynamic, chaotic, and endlessly fascinating. The feeding of black holes is not a simple story of consumption. It is a complex interplay of gravity, energy, and matter, a cosmic dance of destruction and creation that leaves lasting imprints across the universe. In imagining a black hole feeding, one might picture a terrifying beast at the center of the galaxy, surrounded by clouds of glowing gas, spinning disks of blazing matter, and jets of energy that pierce the darkness of space. Yet the reality is even more magnificent. Black holes are engines of transformation, sculptors of galaxies, and fountains of cosmic energy. Their feasts are chaotic, unpredictable, and violent, yet they are essential to the cosmic order, shaping the universe in ways that are both destructive and creative. Every star torn apart, every jet of plasma ejected, every photon flung across space is part of an intricate dance that has been playing out for billions of years. A dance that continues to unfold before the eyes of astronomers who dare to look deep into the heart of the universe. The universe in its vastness may seem eternal and unchanging, but black holes remind us of its restless energy, its capacity for sudden violence, and its endless cycles of transformation. Feeding events are the ultimate expressions of this energy, cosmic banquets where matter is consumed, light is born, and chaos reigns supreme. The echoes of these events reach across light years, influencing regions far beyond the black hole itself, and leaving traces in the form of high-energy particles, radiation, and gravitational waves. In this way, the act of feeding connects the smallest scales of matter to the largest structures of the universe, linking the fate of individual stars to the evolution of entire galaxies. Black holes are not simply objects of fear or fascination. They are central characters in the story of the cosmos, their feeding shaping the narrative of the universe itself. From the supermassive monsters at the hearts of galaxies to the smaller stellar mass black holes scattered throughout space. Each feeding event is a chapter in a cosmic story of grandeur, chaos, and transformation. A story written in the language of gravity and light, and one that continues to captivate, challenge, and inspire us as we seek to understand the universe around us. even as our technology advances, revealing ever more details of these feeding events, there remains an element of mystery, a recognition that black holes operate at the very limits of physics. They test our understanding of space, time, and energy, pushing the boundaries of what is possible in nature. Observing them, modeling them, and interpreting their behavior requires creativity, ingenuity, and courage as we confront phenomena that seem almost magical in their extremity. And yet, the more we learn, the more we realize that black holes are not simply destructive. They are creators, transformers, and orchestrators of cosmic change, performing a role that is as vital as it is terrifying. When most people hear the word black hole, their minds immediately conjure images of a dark, voracious monster, a cosmic vacuum that swallows everything in its path: stars, planets, gas, light itself, leaving nothing but emptiness behind. For centuries, this terrifying perception has dominated popular imagination and even scientific descriptions. Black holes, after all, are regions of space where gravity has become so intense that nothing can escape its pull, not even light. They are often depicted as cosmic devourers, endlessly consuming matter and energy, leaving a trail of destruction in their wake. Yet, as astronomers and astrophysicists delve deeper into the mysteries of these extraordinary objects, a far more complex and fascinating picture emerges, one that challenges this simplistic notion of black holes as mere agents of destruction. It turns out that black holes are not only capable of consuming, crushing, and obliterating matter, but can also act as creators, sculptors, and engines of energy that influence the very structure and evolution of galaxies. Among their most astonishing feats are the colossal jets of energy they launch into the cosmos, phenomena that demonstrate that black holes are not just cosmic endings, but, in a profound sense, cosmic beginnings as well. These jets of energy, often called relativistic jets, because the particles within them travel at speeds close to the speed of light, are among the most spectacular and powerful events in the universe. They are narrow beams of highly charged particles and radiation that shoot out from the region surrounding a black hole, extending for thousands, sometimes even millions, of light years into space. To grasp the scale of these cosmic fountains, consider that 1 light year is nearly 6 trillion miles. Some jets stretch across millions of these light years, far surpassing the size of entire galaxies. Imagine a structure that stretches across distances unimaginable to our daily experience, yet is powered by a single compact region, often no larger than the orbit of Mercury around the Sun. These jets are a paradox of scale and energy, a testament to the extraordinary physics at play near black holes, particularly those that are supermassive, weighing millions or even billions of times the mass of our Sun. The formation of these jets begins in the turbulent, violent environment near a black hole, specifically in the accretion disk, a swirling pancake of gas, dust, and other matter that spirals into the black hole under the irresistible pull of gravity. As this matter accelerates and compresses, it heats up to unimaginable temperatures, often millions of degrees, emitting intense radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. The black hole itself, being a region from which nothing can escape, cannot directly release energy. Yet, paradoxically, it indirectly powers these colossal jets through the motion and magnetic fields of the infalling matter. Magnetic field lines anchored in the accretion disk twist and coil, forming what scientists call a magnetic tower. As these lines become increasingly twisted by the rotation of the disk and the black hole's own spin, they can fling charged particles outward at velocities approaching the speed of light, creating the awe-inspiring focused beams of energy that pierce the surrounding galaxy and beyond. The impact of these jets on their host galaxies is profound, transformative, and surprisingly creative. While the black hole consumes matter at its center, the jets act like cosmic blowtorches, heating surrounding gas, stirring up interstellar material, and sometimes triggering bursts of star formation in regions far from the black hole itself. This dual role of destruction and creation reveals that black holes are far more than simple cosmic trash compactors. They are engines of galactic evolution. Observations of galaxies like M87, a giant elliptical galaxy located about 53 million light-years from Earth, provide striking evidence of this process. At the heart of Métis 7 lies a supermassive black hole, weighing approximately 6.5 billion times the mass of our Sun. From this singular point, a jet of plasma extends nearly 5,000 light-years into space, visible even to powerful optical telescopes. This jet, though powered by a single black hole, influences gas clouds and star-forming regions across vast portions of the galaxy, shaping its structure and evolution in ways that are only beginning to be understood. Interestingly, the energy contained within these jets is not only immense, but also highly focused. Unlike the radiation that floods outward from stars in all directions, the material in relativistic jets is channeled into tight pencil-like beams, allowing the energy to travel extraordinary distances with relatively little dissipation. This means that a single black hole, though compact, can affect regions of space many thousands of times larger than itself. It is as though the black hole possesses a cosmic pen, capable of writing across millions of light-years, sculpting galaxies with invisible strokes of energy. The physics behind this concentration of power is deeply rooted in the theory of relativity, which describes how the fabric of space and time is warped in the presence of extreme gravity. Near a black hole, space-time is twisted and dragged, and when combined with the ferocious rotation of the black hole and the electromagnetic forces of the accretion disk, this produces conditions ripe for the formation of jets that can remain coherent over vast cosmic distances. The influence of these jets is not limited to the galaxies that host them. They can inject energy and matter into the surrounding intergalactic medium, the sparse gas that permeates the space between galaxies. In doing so, they regulate the formation of new galaxies, prevent runaway star formation, and maintain a delicate balance in the cosmic ecosystem. Without these jets, galaxies might collapse under their own gravity, forming stars at an unsustainable rate and exhausting their reservoirs of gas too quickly. In this sense, black holes act as cosmic gardeners, pruning and regulating their surroundings to ensure that galaxies remain vibrant and sustainable over billions of years. Far from being mindless destroyers, they are active participants in the grand dance of cosmic evolution, wielding their power with a combination of ferocity and subtlety that is difficult to grasp fully. The radiation and particles from these jets also provide astronomers with crucial insights into the universe's history and the behavior of matter under extreme conditions. By studying the light emitted from jets at various wavelengths, from radio waves to X-rays, scientists can map the structure of magnetic fields, measure the speed and composition of particles, and test the limits of physical laws in regimes far beyond what can be recreated on Earth. For instance, by observing the jet from the black hole at the centre of the galaxy Centaurus A, astronomers have discovered that the particles in the jet travel at more than 99% of the speed of light. Such observations push the boundaries of human knowledge and offer a glimpse into the extraordinary phenomena that govern the universe at its most extreme. It is important to recognise that these jets are not steady, unchanging streams. They are dynamic, often flickering, bending or knotting as they interact with the surrounding medium. In some cases, they appear to precess or slowly change direction, much like a spinning top wobbling as it rotates. These changes can create shock waves that propagate through interstellar space, compressing gas clouds and potentially igniting new rounds of star formation. Observations of jets in galaxies such as 3C273, one of the most luminous quasars known, reveal knots of bright emission along the jet, indicating regions where particles are being accelerated to extraordinary energies. Each of these knots can act as a catalyst for further cosmic processes, showing once again that black holes are not merely consumers of matter, but facilitators of complex interactions across vast scales. Even more astonishingly, some jets are capable of influencing the large-scale structure of the universe itself. By transporting energy and matter far from their galactic origins, jets can shape the distribution of gas in galaxy clusters, the largest gravitationally bound structures in the cosmos. This energy can prevent clusters from collapsing under gravity too quickly, regulate the temperature of intergalactic gas, and contribute to the formation of filaments and voids that define the cosmic web. In other words, a black hole at the centre of a single galaxy can, through its jets, have an impact that resonates across millions of light-years, affecting the architecture of the universe on the grandest scales imaginable. These jets also illuminate the paradoxical nature of black holes as both destroyers and creators. While they are regions of inescapable gravity, capable of swallowing stars and planets whole, the phenomena associated with them, accretion discs, magnetic fields, and relativistic jets, produce some of the most energetic, organized, and creative events in the universe. In this sense, black holes embody the duality of nature. They are at once terrifying and generative, destructive and constructive, endings and beginnings intertwined. By studying jets and their effects, astronomers are learning to appreciate black holes not merely as cosmic graveyards, but as engines of cosmic innovation, capable of shaping galaxies, fueling star formation, and regulating the very fabric of the universe itself. In recent years, advances in observational technology have allowed scientists to witness these processes with unprecedented clarity. Instruments like the Very Large Array, the Hubble Space Telescope, the Chandra X-ray Observatory, and the Event Horizon Telescope have captured images and data revealing the structure and behavior of jets in extraordinary detail. In April of 2019, for example, the Event Horizon Telescope produced the first ever image of the shadow of a black hole in the galaxy M87, revealing not only the black hole itself but also the base of its jet with remarkable clarity. These observations have transformed black holes from theoretical curiosities into tangible, observable engines of cosmic power, allowing scientists to probe questions that were once considered purely speculative. How do these jets form? How do they remain coherent over millions of light years? How do they influence the evolution of galaxies and galaxy clusters? Each new observation brings with it insights that deepen our understanding of black holes as creative forces in the universe. In the grand tapestry of the universe, black holes are far more than isolated predators lurking in the darkness. Through the power of their relativistic jets, they are architects of galaxies, regulators of star formation, sculptors of intergalactic space, and even messengers of cosmic history. They exemplify the paradoxical nature of existence itself, where creation and destruction, order and chaos, energy and gravity are entwined in a continuous dynamic dance. In this light, black holes are not simply the endpoints of matter and energy. They are engines of transformation, catalysts of cosmic creativity, and in many ways the universe's most unexpected creators. The next time we think of black holes, we might pause to consider that behind the veil of darkness lies not only a force of consumption, but also a fountain of energy and creation. Their jets, stretching across incomprehensible distances, carry the signature of processes that are both violent and generative, destructive and creative, proving that in the universe, even the most fearsome phenomena can be sources of profound wonder and cosmic artistry.